right, I think we can start this afternoon session. So we're very happy to have Nathan Berkovits, who's going to speak about manifest space-time supersymmetry and the superstring. Thank you very much.
Okay, thanks very much for the invitation, and I'm sorry I couldn't be there in person. I'm going to be talking about a paper I wrote a few months ago called Manifest Spacetime Supersymmetry and the Superstring. So there are various motivations. The main motivation is to try to really understand the relation between what's called the RNS Ramon-Nevers-Schwarz formalism for the superstring and the pure spinor formalism. And of course, the Ramon-Nevers-Schwarz formalism is much better understood, but space-time supersymmetry is not manifest, so it has some problems. And pure spinor formalism, at least computationally, is much more efficient. People have computed up to 3-loop superstring computations using the formalism. But there's still some mysteries and trying to understand, there's some subtleties in the multi-loop formalism. And hopefully, by understanding the relation better between the two formalisms, that will be useful for trying to understand these subtleties better. So, of course, the RNS formalism has manifest worldsheet supersymmetry, and it does have D equals 10 spacetime supersymmetry, but it's hidden or not manifest. That makes it difficult not only to compute scattering amplitudes because the cancellation is coming from supersymmetry, but even to describe Ramon-Ramon backgrounds, which of course are necessary if you want to describe anti-de Sitter space. So the pure spinor formalism is in some senses the opposite. So the spacetime supersymmetry is manifest, but the local worldsheet supersymmetries, although they're present through a BRST operator, they're hidden. They're certainly not manifest. And the cancellations from the supersymmetry are manifest, but as I said, there's some subtleties coming in multi-loop, which, although there are some tools for trying to deal with them, certainly they're not well understood. So going beyond 3-loop, so what has been computed up to now has been 3-loop computations using the pure spinor, just the first term, so the term at low energies. Going beyond that to get the full 3-loop amplitude is still an open problem. And of course, in RNS, one has only been up to go up to 2-loop. So, so although pure spinor form is more powerful, one would like to even do better. So what I'm going to discuss here is a generalization of the Ramon-Nevers-Schwarz formalism, which has manifest spacetime supersymmetry. And the idea is that this generalization is going to be somehow some intermediate formalism between the RNS and the pure spinor formalism. And hopefully will help not only to understand better the RNS formalism, but also to understand better the pure spinor formalism and these subtleties. So please interrupt me. So the sound system is very good. So congratulations. I think doing a hybrid conference is very difficult. And so please interrupt me whenever you want with questions. You don't have to raise your hand. Okay, so let me start by just reviewing the different formalisms. So the RNS formalism, of course, we have X's and psi's, and we also have the BC and beta gamma ghosts. And Ramon-Nevers-Schwarz sectors are when the psi's are either have periodic boundary conditions or anti-periodic boundary conditions. So the BRST operator is a standard BRST operator, which you can write for any n equals 1 superconformal field theory. And then a flat background that just has the form here. And then the gluon and gluino vertex operator. The gluon vertex operator, essentially you can just read off from the BRST operator, just essentially tells you how, so for example, dx is just the translation operator and psi is related to the Lorentz generator. But the gluino vertex operator is, of course, much more complicated. So in the RNS formalism, the Nevers-Schwarz sector is very simple to describe. It just essentially comes from n equals 1 superconformal field theory. But to discuss the Ramon sector or the space-time fermions, you need to bosonize the ghosts. So this was done by Frieden, Martinek, Schenker 15 years after the formalism was developed. So you have the beta gamma ghosts here, which we're going to fermionize. So these are bosonic ghosts, but we're going to fermionize them by writing them as in terms of these 8 and psi fields, which are free fermions, and this chiral boson phi. And then the spin field here, so this is a space-time spinor, and you can explicitly construct it by bosonizing the 10 psi's into 5, so you split them up into 5 complex pairs, and then you bosonize them. And essentially you construct the spin field out of these chiral boson sigma. So the gluino vertex operator is much more complicated than the gluon vertex operator, and that makes it difficult to describe Ramon-Ramon backgrounds, because the gluon vertex operator, the ghosts and matter fields essentially decouple, but in the gluino they couple just because you have to bosonize all these ghosts here. So, of course, space-time supersymmetry is also not manifest just because the Navier-Schwarz and Ramon sectors are, of course, related by space-time supersymmetry, but the vertex operators have such a different form that it's difficult to see how to make space-time supersymmetry manifest. Okay, in the 80s was developed Green-Schwarz formulas, which I'll call Green-Schwarz-Siegel, because he played an important role in describing this kappa symmetry. And also, the way I'm going to describe it, I'm going to use a first order form for the theta. So we have the conjugate momentum to theta, which I'll call P alpha. So theta and P, of course, are now space-time spinors and world sheet fermions. So I guess sorry, I said it wrong. They're space-time spinors, but theta is going to be a world sheet scalar, and P alpha is going to be a world sheet vector, if you like. The X's, of course, are world sheet scalars. And Green-Schwarz, they weren't able to covariantly quantize, but of course you can introduce a BC ghost if you want. And the BRST operator that one can construct is constructed essentially from the X's and thetas. You can construct this space-time supersymmetric form of X and theta, which is invariant under the space-time supersymmetry. So the space-time supersymmetries are just here, it's just delta theta is just shifted by a constant, and delta X is shifted by that amount, just like usual 10-dimensional space-time supersymmetry. And the space-time supersymmetry generator can be written as this Q alpha. So Q alpha, of course, commutes with all the space-time supersymmetric objects. So another space-time supersymmetric object, which is convenient to define, is this D alpha. So D alpha is constructed from the canonical conjugate to theta. So the canonical conjugate to theta I'll call P alpha. So that plays the role of DD theta. And then small d alpha is something like the covariant derivative. So if you were thinking in superspace, you would write something like capital D alpha is equal to DD theta plus theta gamma alpha TDXM. So the world sheet version of this is this small d alpha, just because dx here plays the role of ddx. And this satisfies a commutation algebra, which is if you take the Poisson bracket of d alpha with itself, you get something which is non-zero, which is just pi m. So that's the space-time supersymmetric version of x. That means that small d alpha has both first class and second class constraints. So pi is not the first class constraint, but pi squared is the first class constraint. So that means that small d alpha has first class and second class constraints, which we can quantize in light cone gauge. But covariant quantization of this theory is still an open problem. So although space-time supersymmetry is manifest, so all the BRST operator and the action is, of course, manifestly space-time supersymmetric, the BRST operator is not enough to quantize the theory. You also need these second-class constraints. Okay, now as I mentioned, you can also, of course, compute the anti-commutator of Q alpha with Q beta. That's also not zero. Of course, it's not supposed to be zero. It's supposed to generate the supersymmetry algebra. And in this case, Q alpha with Q beta generates the translation generator. Now that's different from in the RNS formalism. If you compute Q alpha in this description, one can also construct a Q alpha. So Q alpha is essentially just the zero mode of the Ramon vertex operator. So it's something like dz e to the minus phi over 2 sigma alpha chi alpha. Sorry, there's no chi alpha. That's a space-time supersymmetry generator, what's called in the minus a half picture. But as we'll see, Q alpha with Q beta in the RNS formalism is not the usual space-time supersymmetry generator. It's not equal to dx gamma m alpha beta dx. That's essentially one way to see that space-time supersymmetry is not manifest. So that's essentially the disease we're going to cure in this generalized RNS. But before doing that, let me say something about the pure spinor formalism. So the pure spinor formalism has similar variables to Green-Schwarz in the sense that it has this x and theta and the conjugate momentum to theta, but it also has these ghosts. So these are bosonic ghosts. So if you want, you can think of the bosonic ghosts as coming from gauge fixing this kappa symmetry. So here we had a symmetry coming from these d alphas. So the d alphas describe first and second class constraints. The first class constraints are usually called kappa symmetries, and you can think of the lambdas somehow being ghosts for these kappa symmetries. So that's why they're bosonic ghosts. But they satisfy a constraint, which is why they're called a pure spinor. So in 10 dimensions, a pure spinor is a spinor. So alpha is 1 to 16, 10 dimensions. But because lambda satisfies this constraint, only 11 of the 16 components of lambda are independent. So Cartan called this a pure spinor in 10 dimensions. Now the BRST operator in this formula is constructed from the pure spinor ghost times the constraint. So that's natural if you want to think of a BRST operator as being the ghost times the constraint. But the unusual feature is that D alpha is not the first class constraint. So normally to construct a BRST operator, you need first class constraints. And essentially the fact that this has second class constraint piece in it is essentially canceled by the fact that lambda is a pure spinor. So because of this pure spinor constraint, if you compute Q squared, you get lambda gamma m lambda times pi m. And because this is 0, that means that Q squared equals 0. So that's essentially the new feature of this pure spinor formalism. But the action is essentially the same as in the BRST operator, but you also have, of course, a contribution from the ghosts. So the action in a flat background, this formalism is just dx d bar x plus p alpha d bar theta alpha. And then there's a coupling of the w's with the lambdas. So w is the conjugate momentum to lambda of conformal weight 1. So these have conformal weight 0. And this has conformal weight 1. And the BRST operator, as I mentioned, is how it's constructed from these fields. So lambda alpha, d alpha, remember, is defined in terms of these fields in this way. So it's the same definition as d alpha as we had in the Green-Schwarz-Siegel formalism. Oops, sorry. And the BRST operator and the action are, of course, manifestly space-time supersymmetric, using the same supersymmetry transformation as we had before. Now, in this formalism, the BRST operator is, of course, not the usual one. It doesn't have the BC ghosts, but you can still use it to define physical states. So you can ask, what's the cohomology of this operator? And you find it ghost number 1. It describes the usual, if we're just doing the open string. It describes the super Yang-Mills states, but now it does it in a way which is manifestly space-time supersymmetric. So it does it in superspace. So A alpha is a superfield, and you can gauge it to have the form where the lowest component is linear in theta, and that's just the gluon. And the term quadratic in theta is the gluino, and then the higher order terms are just derivatives of those. So this is called the super Yang-Mills spinor potential. And this would be the unintegrated version of the vertex operator, and the integrated version is what I call U. And that starts out with similar terms as in the RNS vertex operator, namely the gluon coupling is similar. It couples to dx, or more precisely the space-time supersymmetric version of dx. And then you can also work out what the gluino couplings are. So the vertex operators are relatively straightforward. Of course, they're all written in superspace. You can use these vertex operators to compute, as I mentioned, up to genus 3 amplitudes. Okay, so that's essentially a review. Of course, we can also do Ramon-Ramon vertex operators by taking the closed version of this, which is just you take the left-right product of two open string vertex operators. And that, by adding that to the flat action, you can just construct Ramon-Ramon backgrounds in a straightforward way. Okay, so that's essentially a review of these three formalisms. Before I go on to the next part, are there any questions? Okay, so now let me talk about how to make the RNS formalism manifestly space-time supersymmetric. So as I mentioned, the usual supersymmetry algebra is this Q alpha with Q beta equals PM. And space-time supersymmetry can be made manifest if the algebra closes without using equations of motion. So this is familiar to anybody who studies space-time supersymmetric systems. So a simple example is, for example, just a scalar multiplet in 4 dimensions, or the Wess-Zumino multiplet. So it consists of a 4-dimensional complex scalar phi and phi bar, and then the spin 1/2 fields chi and chi bar. And if you just write the standard, let's just do free action first. So d4x. Now we're in 4 dimensions. Okay, so you have d4x, dm phi bar, plus chi. I'll write it using Pauli matrices, so you have something like this. So there's the free action. And you find that it is space-time supersymmetric, and where these are the ways that phi and chi transform under space-time supersymmetry. But you find that the algebra doesn't close without using equations of motion. You compute Q alpha with Q beta. So if you compute, well, I'm not going to try to do it. If you compute Q with Q bar on chi, you find that it closes only if you use the equations of motion d slash chi equals 0. So the well-known way to solve that is to add auxiliary fields. So these f and f bar are scalar fields, which you add to the action just by adding the term ff bar. And now you find that the supersymmetry relations, if you include these terms in the space-time supersymmetry variation of chi and f, you find that the algebra now closes without using equations of motion. And you can, of course, make space-time supersymmetry manifest by combining phi and chi and f into a superfield. And then you can write this action as d4x, d4 theta, phi bar, so d squared theta bar, phi bar. Okay, and you can also, of course, add interactions by adding things like f of phi. So this is the usual f term plus complex term. So this is, of course, well known for anybody who studied 4-dimensional supersymmetry. And the key ingredient is adding these auxiliary variables. So in the RNS formalism, we tried to do the same thing in the RNS formalism, as I already mentioned. The space-time supersymmetry generators have this simple form. It's essentially the fermionic vertex operator at 0 momentum. And when you take the anti-commutation, you find that you don't get dx. You get this object here, which is, you can think of it as the translation generator in the -1 picture. So in RNS formalism, one has this notion of picture. Which is essentially counting the dependence on this phi field. And more precisely, it's defined as d phi minus xi eta, where, remember, phi and xi eta are described here. So with this definition of picture, beta and gamma carry picture 0, but this carries picture -1, because there's an eta minus phi. And the way to get, the way to relate this algebra with the supersymmetry algebra is to use picture raising. So to do that, we have to introduce this notion of what's called Hilbert's small and large Hilbert space. So the small and large Hilbert space is defined as states which are either independent, small Hilbert space is states which are independent of the zero mode of psi, and the large Hilbert space are the states which depend on psi. And physical vertex operators in the RNS formalism are essentially built out of the beta and gamma ghosts, which don't depend on the zero mode of psi. So they are defined in the small Hilbert space. So they're annihilated by not just the BRST operator, but by the zero mode of the eta ghost. Now, you can, in RNS, you can describe states which are in different pictures by hitting with what's called the picture raising operator, which is the BRST operator acting on the Xi0 mode. So this was, of course, discussed by Friedan, Martinek, and Schenker. And the reason why this is non-trivial is because in the small Hilbert space, the Xi0 mode is not allowed. Otherwise, this would, of course, be BRST trivial. So it turns out that this object here, which you get from the spacetime supersymmetry algebra, is related to the usual translation generator by picture changing. That means that you do this picture changing operation. Essentially, you multiply this by the Xi0 mode and take Q of it. And that's the picture raising operation, which takes this object into the translation generator. Now, picture changing involves this BRST operator, and BRST operator can only be defined, it's only, so picture changing is only a well-defined operation if all the states are on shell. So in other words, picture changing does not affect the scattering amplitude if all the states are on shell. So that's equivalent to saying the supersymmetry algebra requires the equations of motion to close. So in that sense, we're in the same same situation as we had here before adding these auxiliary variables. So now what we're going to do is we're going to add some auxiliary variables to the RNS formalism in such a way that we remove this problem. So this is going to be a generalization of RNS, which is going to involve some additional variables. That's why it's called a generalization of RNS. And these additional variables are going to play the role of these auxiliary fields that we needed to make spacetime supersymmetry manifest. So before telling you what the different steps are, so we're going to need 4 different steps here to make spacetime supersymmetry manifest. First of all, we're going to have to work in the large Hilbert space, so the Hilbert space including the Xi0 mode. Then we're going to add these auxiliary variables. Then what we're going to do is just going to modify the spacetime supersymmetry generator by adding something which is BRST trivial. So that, of course, does nothing when it acts on shell states. And finally, we're going to perform a similarity transformation, which is going to relate this modified supersymmetry generator to the same supersymmetry generator we had in the Green-Schwarz-Siegel forms, which is the same as in the pure spinor. Okay, so let's do these 4 steps. Maybe before, are there any questions up to now?
I have a request, which is, could you use a darker color for annotating?
Yep. Thanks. Any other questions?
Can you make this analogy? Can you spend a couple more minutes on the analogy, please, between the
Yeah.
So I guess maybe what I'm not understanding is that in the 4D, the standard Westerino story that you had,
Yep.
it's just purely classical, right? It's just a classical field.
Yep.
In the RNS, you kind of, well, you talk about Hilbert spaces, picture changing, and so on. So you're in the first quantized formalism. Well, maybe you just say a few words about this. I'm confused.
Yep. Well, I'm just going to discuss it here. So, of course, the Poisson brackets are the same thing as like the classical spacetime supersymmetry generators, right? When you talk about quantum effects, I guess what you're thinking if there's some kind of anomalies or something like that to the Poisson brackets. But I'm really just discussing the classical spacetime supersymmetry transformation, how they act on the worldsheet variables. So I don't think I'm discussing, so picture changing is, maybe we can discuss this in about 10 minutes after I discuss what these auxiliary variables are. So maybe things will be more straightforward then.
I think I was trying to get the component fields and so on, but.
So I'll tell you what,
So,
let's wait. Let me just wait until I introduce the auxiliary variable. So this might be a good question to ask at the end also, but I hope you don't need to know this just to try to understand what's going on. So let me just say a little more about these 4 steps. Okay, so if we're in the large Hilbert space, then of course the BRST operator is not enough to define the cohomology. We need both, it has to be both annihilated by A to 0 and by QRNS if we're in the large Hilbert space. But one way to implement this in a large Hilbert space is to consider the cohomology of Q prime, which is equal to the difference of QRNS and A to 0. So if something has a fixed picture and it's annihilated by Q prime, then it has to be annihilated by both QRNS and A to 0. And it turns out if it has anything but infinite picture, so if it has, it can be a sum of different pictures. It doesn't have to just be in a fixed picture, but if it has a picture, if all the terms in the state have finite picture, then you can show that the cohomology of Q prime is actually equal to the small Hilbert space. Now, if you work in a large Hilbert space, then and using this Q prime, you can understand picture raising as a BRST trivial operation in this following sense. So if I start with a vertex operator in one picture, and I add to it Q prime of C times V, so the term QRNS, when it acts on this, just gives the picture raised version of V. Whereas the A to 0, when it acts on this, just gives you minus V. So this cancels this. Then we're left with the picture raised version of the vertex operator. So if we work in a large Hilbert space and modify the BRST operator to be the difference of these two, then the cohomology of Q prime is just the cohomology of states in a small Hilbert space. And I'm assuming that the picture is finite again. Are there any questions about that step? Okay, then the next step is to add auxiliary variables. So what we're going to do is we're going to add a set of fermions and bosons in such a way that they don't modify the cohomology. So this would be similar to adding the auxiliary variables F and F bar, which don't propagate. So the way you're going to modify the BRST operator is by adding this topological term here, lambda alpha p alpha. So this is the standard topological quartet mechanism, which tells you that physical states are independent of the thetas and p's and the capital lambdas and omegas. Any question?
So what's the nature of these auxiliary variables? They're not worldsheet fields.
Yes, they will be worldsheet variables. So the action, let me write it down. I have space. So the action will be the original action, it's called S0. So this is our SRNS. So let's just do the holomorphic version. So that's going to be omega d bar lambda. So in a flat background, they just have this ordinary first order action. Okay? So the holomorphic. Now, if you're doing type 2, of course, you'd also have the right moving version. Okay, and they appear in the BRST operator in this way. So of course, the term we added in the action, this term here, is actually BRST trivial. So you can write it as just Q of Q squared C. So remember, the BRST operator had the term lambda alpha p alpha. So this, I guess you can write it as omega t bar theta. So you're adding a BRST trivial term to the action. Okay, any other question? Okay, so now we've added auxiliary variables. Now we're going to modify the space-time supersymmetry generator. So here was the original space-time supersymmetry generator. And now we're going to add Q prime of, I'll call it sigma alpha. So sigma alpha is just a combination of the variables I introduced. And of course, when acting on on-shell states, this term does nothing. So it's analogous to doing what we did for the four-dimensional case here, adding these additional red terms in the space-time supersymmetry transformations. Okay? So it modifies the space-time supersymmetry transformations, but in a way which doesn't affect on-shell states. So we're here. And now you can verify using these modified small q that the usual space-time supersymmetry algebra is satisfied. So what we've done is we've enlarged to the large Hilbert space. So now picture raising is a gauge transformation. Of course, using equations of motion, it's a gauge transformation. And then we've modified the space-time supersymmetry transformation in such a way that the on-shell transformations are, that on on-shell states, nothing's changed. But now the algebra closes without using picture raising. So now you can try to make the theory manifest as space-time supersymmetric because the space-time supersymmetry algebra closes without using equations of motion. Finally, we're going to form a similarity transformation. So the similarity transformation is generated by this R. And that's also, of course, going to form the same similarity transformation on the BRST operator. But when you do it on this space-time supersymmetry generator, you find that it just takes the form of the Green-Schwarz-Siegel space-time supersymmetry generator. So now the space-time supersymmetry transformations are precisely the same as they were in the Green-Schwarz or in pure spinor formulas. But of course, the BRST operator is also changed. So after performing the similarity transformation, the BRST operator, which started out as being the RNS BRST operator plus this topological term, now has, of course, also a manifestly space-time supersymmetric form because it's now also going to, of course, commute with Q prime, with small q prime. So I call this modified RNS. So this is, of course, 0, which means that all the terms here are manifestly space-time supersymmetric. And you can work it out, and this is the form they have. So it has the usual RNS term, gamma psi m dxm, but of course now everything has space-time supersymmetry. It has some unusual terms. For example, it also has this term, psi e to the minus phi. Psi e to the minus phi, that's equal to 1 over gamma. So gamma was 8 e to the phi. So the inverse of that is psi e to the minus phi. So it's unusual, but it's manifestly space-time supersymmetric, and it's straightforward, for example, to write down vertex operators in the cohomology. And now, of course, you can write them in terms of the d equals 10 superfields. So these are the vertex operators. And so the vertex operator starts out similar to the unintegrated vertex operator. Remember, in the pure spinor formulas, on the unintegrated vertex operator, let me use red, was lambda alpha A alpha. So now it's capital lambda. I should have stressed this. Capital lambda is unconstrained. It's just a 16-component spinor, whereas small lambda is a pure spinor. So it does look a little bit like the pure spinor formula, but it also has a term which this term, of course, looks like the unintegrated vertex operator in the RNS formula. Okay, and then you also have B and C dependence. The integrated vertex operator you obtain by essentially taking the term in the unintegrated, which is proportional to C. So this would be the integrated vertex operator. Okay, so one can check that this vertex operator, blue vertex operator, is in the cohomology of this modified RNS BRST operator. So it's manifestly space-time supersymmetric. If you look at how the gluon appears, so we're doing, of course, the open superstring. So this has the gluon and gluino if you're looking at the massless sector. So the gluon vertex operator is not so different from the RNS vertex operator. So the gluon vertex operator, you just look where the gluon appears in these superfields here. And you find that at lowest order in theta, of course, you have this term here. That's this term here. Then the terms proportional to C, you get a term here coming from here. And then the psi term comes from here. But now you get some additional terms. So these additional terms here involve the auxiliary variables. But they appear in a way which cancel in computations. That's just because essentially you have 16 capital lambdas, you have 16 thetas. And because these carry the same level, they essentially cancel because you have bosons and fermions which cancel when you do the OPEs. Now there are high order terms in thetas which will not contribute to the amplitudes, at least if you're looking at gluon tree amplitudes. That's just because there are no conjugate variables, so these small p's to cancel the thetas. So the gluon vertex, it's relatively straightforward to see that, at least for tree amplitudes, the amplitudes are the same as in the RNS formalism. Essentially, all the theta dependence just drops out, and this dependence here just gets canceled because of fermion and boson cancellation. Okay, but the gluino vertex operator is now very different. So the gluino vertex operator is, of course, the terms which have an odd number of thetas or are fermionic on the Wiltshire. So there's no spin fields anymore. And of course, I'm only discussing here the GSO projected sector. So I'm not, in the RNS formalism, of course, you can also have tachyons if you look at the GSO1 projected sector. So everything I'm saying here is just the GSO projected sector. And in that case, it's easy to see that everything is independent of the spin field. So I won't have time to discuss this, but if you want, you can also discuss, for example, what happens to the tachyon in this version of the RNS formalism. What you would find is that in order to describe the tachyon, you need to construct a spin field not out of the psi's, but a spin field out of the thetas. So the thetas would need to have unusual boundary conditions if you want to describe the tachyon. One way to see that is that you know that the tachyon is supposed to have square root cuts with the space-time supersymmetry generator. Space-time supersymmetry generator is now just essentially P plus dx slash theta. So the only way that's possible is if it has square root cuts with these variables. And once it has square root cuts with these, you also need square root cuts with these, just because in the BRST operator, they come together. Okay, so that's a discussion of how we're going to make space-time supersymmetry manifest in the RNS formalism. And then the next step is to relate this to the pure spinor formalism. But before I do that, now maybe I can go back to the questions that were asked about classical versus quantum. I don't know if you want to re-ask the question or it became clearer now.
No, that's fine actually. No, it was just to think aloud. That's what I asked. Okay, so it's fine then.
Okay, so I mean, all of this is in the paper, but I'm happy to discuss and ask questions. Of course, we can do it at the end also. But are there any other questions about this? Okay. Okay, so now we have this formalism in which space-time supersymmetry is manifest. The vertex operator for the Nivard-Schwarz sector is slightly more complicated. The vertex operator for the Ramon sector, I think, is much simpler than in the RNS formalism. But of course, what we want to do now is we want to use this to try to relate it to the pure spinor formalism. So in the RNS formalism, of course, we have fields which are half integer spin, which are these psi's and also the beta gamma ghosts. And that requires summing over spin structures. Whereas in the pure spinor formalism, all the fields have integer spin, which of course removes the need to sum over spin structures, which is why it's much simpler to do higher genus computation. But now, if you want to relate the two, you have to do some kind of twisting because you somehow have to get rid of the half integer spin. And the way we're going to do this is we're going to twist the psi's into fermionic fields which have just integer spin. So of course, if we didn't have pure spinors, that would break Lorentz symmetry. So we have to choose 5 complex pairs of the psi's, which of course breaks the SO10 down to U5. But because we have the pure spinor essentially parameterizes how you break SO10 to U5. So with the help of the pure spinors, which I'll call lambda and lambda bar, so lambda is the pure spin we had in the pure spinor formalism. Lambda bar, for the moment, let me just think of it as a constant spinor. When we do the non-minimal pure spinor formalism, it will turn out to be a dynamical variable. But at least in this talk, I want to restrict lambda bar to be constant just to simplify things. In the paper, I discussed the case in which it's a dynamical variable. Okay, so using lambda and lambda bar, so I'm going to assume that if you contract lambda with lambda bar, that's non-zero. And that's essentially related to a subtlety in the pure spinor formula. So lambda alpha, lambda bar alpha, I'm going to assume this is fixed and that it's chosen such that this contraction is non-zero. So of course, if I want to do this on the whole pure spinor space, I need to choose patches. So you can't do this globally on the pure spinor space, but you can do it locally in the sense that you can choose patches where for a fixed lambda bar, at least there's a set of lambda alphas or a patch of lambda alphas such that this is non-zero. Okay, so using lambda and lambda bar, I'm going to define how I twist my psi's. So these capital gammas will have a conformal weight 0 and capital gamma bars will have conformal weight 1. So that's just because of this, one is multiplied by gamma and the other is divided by gamma. So psi, of course, you can invert this to write psi in terms of the sum of capital gamma and capital gamma bar. And we're also going to decompose this auxiliary variable, capital lambda, into a pure spinor and an additional variable, which will be a vector. So lambda and u are bosonic variables. And you can show, I already mentioned that there are 11 independent components of the pure spinor, and 5 of the 10 components of this vector will appear if I contract it with gamma m lambda bar. So these 16 components can be used to decompose an unconstrained 10-dimensional spinor. Yes, question?
So by twisting, sorry.
Yes.
So by twisting, you just mean that you multiply psi with gamma.
Yep. So I'm not doing that. I haven't told you anything about the superconformal generators. It turns out that there is a way to understand, of course, the RNS formalism, before adding these auxiliary variables, had an n equals 1 superconformal generator. So let's find a place to write it. So we had G. And when you do this twisting, it's natural to think of this splitting into G plus and G minus. This is equal to dxm gamma m, and this is equal to dxm gamma bar m. But, I mean, this is a useful idea, but I'm not going to discuss this here, essentially, because after introducing the auxiliary variables, this n equals 1 superconformal generator is unclear. So remember, the BRST operator in this RNS formalism, after you generalize, it has a term, let me find it. Sorry, here it is. So it has a term here which looks like it comes from n equals 1 superconformal generator, but it also has this term. So it's not so clear how to describe the twisting in this language once we add these auxiliary variables. Okay, but in any case, in this case, I just mean by twisting, I mean just twisting the psi's into gamma and gamma bar, and not discussing the superconformal generator. Okay, so what we've done now is we've introduced variables of just integer spin, So we've taken the psi's and split them up into fields of integer spin. And we've also taken the unconstrained bosonic spinor and split it up into a constrained bosonic spinor, a pure spinor, plus a vector. And now what happens is that after doing this twisting, only even powers of gamma appear. So assuming, of course, we're just talking about the GSO projected sector. Then after doing the twisting, essentially, since all the fields are integer except for the beta gamma ghosts, you know that the beta gamma ghosts also have to appear in integer combinations, which mean that only even powers of the gammas appear. So we're going to now define gamma hat to be equal to gamma squared. So of course, gamma had conformal weight minus a half. So gamma hat will have conformal weight minus 1. So now the ghosts, which I'll call beta hat and gamma hat, also carry integer spin. So they carry the same type of spin as the BC ghosts, but they have, of course, they're bosonic. Okay, so gamma hat has conformal weight minus 1 and beta hat plus 2. And I can also fermionize beta hat and gamma hat in the same way as I did before. And what you find is that there's a nice relation between the hatted eta and the RNS variables. So what you find is that eta hat, which is the fermionic, after it comes from fermionizing gamma hat, is just equal to lambda alpha, the pure spinor, times what we were calling Q alpha, just more precisely the BRST current, the space-time supersymmetry current, which was e to the minus phi over 2 sigma alpha. So there's a simple relation between these hatted variables and the RNS variable. And now the final step is to just write the RNS BRST operator in terms of these twisted variables. And that's going to be related to the pure spinor BRST operator, at least after performing a similarity transformation. So what you have to do is you just take the BRST operator, so this BRST operator here. Sorry, I keep going too far. So here's the BRST operator. We're going to just use these twisted variables which have integer spin and write everything in terms of them. So in terms of the hatted ghosts and the gammas and gamma bars. And then what we find is we get something which is very similar to the pure spinor BRST operator after performing a similarity transformation. So R prime is this complicated similarity transformation, but after performing it, what you find is that the pure spinor and this vector that came from decomposing capital lambda, remember capital lambda is decomposed into small lambda nu, these separate into just lambda alpha times d alpha, and um just multiplies gamma bar m. So gamma bar m, remember, was just half of the size. So now what happens is that these fields decouple. So remember in the RNS formalism, the fields which decoupled, which had this topological term, were the thetas and the capital lambdas. In the pure spinor formalism, what you find is the fields which decouple are these u's and the twisted gammas, and also the ghosts. So remember now the BC ghosts and the beta hat gamma hat ghosts have the same conformal weight. They just have opposite statistics, and they also form this topological sector. So after doing this twisting and performing a similarity transformation, you just get back the pure spinor formalism, but now in terms of just the integer variable, the twisted variables. Okay, so that's essentially how to relate this RNS to the pure spinor formalism. And of course, when you do this twisting and writing the variables in terms of the integer spin, you find that the vertex operators we had before also reduce to the pure spinor vertex operators, plus of course something which is BRST trivial. So up to a BRST trivial operation, one finds that the vertex operators also map into each other. Okay, so this is what was done in this paper, and of course the next step is to try to compute scattering amplitudes. Okay, before I go to the next step, are there any other questions? Okay, so scattering amplitudes are more complicated because, of course, in the RNS formalism, we have this superconformal language of computing scattering amplitudes. In the pure spinor formalism, we do have a mechanism for computing scattering amplitudes, but it involves introducing regulators, which I'm happy to go into during the discussion session, but I don't want to talk about it yet. Okay, so let me just conclude and then I'll say something about scattering amplitude. So manifest spacetime supersymmetry is, of course, useful for simplifying computations and it seems to be necessary for describing Ramon-Ramon background. In the RNS formalism, the algebra closes only up to picture changing. But as I showed by working in the large Hilbert space and adding auxiliary variables, you can get the supersymmetry algebra to close without picture changing. So this is not surprising in the sense that we do this all the time if we're working with field theories. Okay, now in this formalism, the vertex operators, at least for the GSO projected sector, can be written in superspace, so in terms of the usual 10-dimensional superfield. So this is, of course, very different from the RNS formalism. It turns out for GSO unprojected states, you can't do that. You have to introduce spin fields. But so in some sense, the RNS formula is more natural if you want to describe the Navier-Schwarz sector, either in the GSO projected or unprojected sector. Whereas this description is much more natural if you want to describe both the Navier-Schwarz and Ramon sectors, but only in the GSO projected sector, which is, of course, what we're interested in if we're doing supergravity. Okay, finally, after twisting this half-integer spin fields in this modified RNS formalism and defining this hatted ghost as being the square of the unhatted ghost, we were able to relate the formalism to the pure spinor description. Okay, so what are some possible applications? So, of course, one might want to describe Ramon-Ramon backgrounds using this modified description. So, of course, we know how to describe Ramon-Ramon backgrounds using the pure spinor formalism, but there's interest in trying to use this RNS description for describing Ramon-Ramon backgrounds, just because some things we understand better in RNS. So, of course, one can do this now because the Gluino vertex operator or the Ramon vertex operator and the Ramon-Ramon vertex operator, which is just the left-right product of the Gluino vertex operator, no longer has spin fields. It no longer mixes the ghosts and matter fields. So it should be completely straightforward to write down now this description in Ramon-Ramon backgrounds. Okay, more ambitious thing one would like to do is to prove equivalence of the amplitude computation. So as I mentioned, if you're doing Navier-Schwarz computations, at least tree amplitudes, it's completely straightforward to show equivalence. For Gluino or for tree amplitude computations involving Ramon sector, it's not trivial even for tree amplitudes, just because the vertex operators are very different. But suppose we just stick to Navier-Schwarz scattering. So at tree level, it's trivial to show that they're equivalent. What about at loop level? So as I mentioned, the vertex operators are very similar, but the objects that come in when you're doing homogeneous computations look different. But of course, this formalism, if it's correct, should be also be useful for showing the multi-loop equivalence. And there we see that there are different subtleties in the RNS formalism. So in the RNS formalism, we know that local worldsheet supersymmetry means that you have to actually integrate over super-Riemann surfaces, which involve both bosonic and fermionic moduli. And we know the integration over the fermionic moduli can be reproduced by introducing these picture raising operators, which are essentially the same operators we already discussed. And when all the states are on shell, then of course, moving these picture raising operators is a BRST trivial operation. But if you're doing homogeneous surfaces, although it's BRST trivial, it can contribute surface terms. And of course, taking account of these surface terms is a complication in RNS, but it's actually interesting and people know how to do it. But it's a subtlety in the sense that the method for keeping track of these surface terms gets more and more complicated as you go to higher and higher genus. However, for certain types of amplitudes, you can show that these surface terms don't contribute. These are what's known as topological amplitudes, and they involve essentially scattering amplitudes where the amplitudes preserve a subset of the space-time supersymmetry. So you can think of them as F terms. In the pure spinor formalism, there's similar subtleties. So I didn't discuss it, but if you work in these patches, it turns out that you need to be careful about when you go off the patch, what happens when lambda lambda bar equals 0. And it turns out that when you do multi-loop amplitudes, you have to work with operators which have explicit poles when lambda lambda bar equals 0. So such as this B goes. And these poles cause subtleties. And again, in principle, one knows how to work with these subtleties, but life gets very complicated. And as I mentioned, for genus 3, it turns out that if you want to go beyond the low energy scattering of 4-point amplitudes, you need to take care of these subtleties. Now, somehow, if one could prove equivalence, these two types of subtleties must be, well, maybe they're not related to each other, but at least you should be able to relate the scattering amplitudes to each other. So you should be able to understand one subtlety using the different formalism. One clue that that's possible is that at least these divergences that come from poles when lambda lambda bar equals 0, they don't occur again for amplitudes which preserve a subset of the space-time supersymmetry. So again, for these F terms, essentially, you don't have subtleties in the two formalisms. And that's a clue that there should be some relation between these subtleties. Okay, so that's the end of my talk. So I'm happy to stop for questions now.
Any question? So maybe I have a question, which is probably not really a question, but more of a curiosity. So do you think, is there a way, for example, to detect somehow from this kind of formalism something like, so for example, non-projectedness of the super moduli space, which is something that actually affects the computation of amplitude in the RNS formalism. So there might be a relation like this.
I'm sorry, so you were talking about the super moduli space of the RNS formalism? Is that what you're asking about?
Yeah, exactly. Like, well, we know that some issues, some difficulty arises in computation of amplitude in the RNS formalism due to the fact that the supermoduli space is non-split or non-projected. So
Yes.
I was wondering whether there is you can actually see something like that, given that you can relate the RNS formalism to the superspace pure spinor formalism, if there's a way to see something like that, say, in the other part, in the other business.
Yeah, I think so. So that's essentially these subtleties that I was mentioning about. So one way to think about this non-splitness is these surface terms. So the point is that the relation of the integration over the fermionic moduli and the picture raising operators, if the space is split, then it's trivial to understand how to work with these picture raising operators. Whereas if it's non-split, then it turns out you need to be careful. You need to split the moduli space up into different regions, and the picture raising operators will be in different places when you do when you split up into different regions. And there's the whole formalism that was worked out recently by Sen and Witten and how to glue these different regions together. And that's what I meant by these subtleties in the RNS formalism. So the hope is, yes, that these subtleties in the RNS formalism will be related to these subtleties in the pure spinor formalism coming from these poles when lambda lambda bar goes to 0. And I guess what I wanted to say is that for these topological amplitudes, for these F term amplitudes, this splitness is not an issue. So there's certain amplitudes you can compute at higher genus, even infinite genus, at which you don't need to worry about the fact that the moduli space is not split. So I'm not claiming that I will be able to, in some sense, resolve the subtlety in the sense that there will always be the subtlety in RNS about the space being non-split. But I think this equivalence, at least you may be able to understand it in terms of a different language in which it comes from these poles when lambda lambda bar goes to 0. So that's the hope. I don't know if I answered your question.
Yes, yes, of course, absolutely. I mean, that would be very nice for me. I'm more into the, say, algebraic geometry part of this business, so I look at this problem from the supermoduli space point of view. So that would be awesome. Thank you very much.
Yeah, there was some paper. So there were some papers which I don't. So another way to try to answer your question, which I think has not been studied very much, is why in the RNS formalism these subtleties do not appear when the when the amplitudes preserve a subset of the space-time supersymmetry. So there was some papers by Albert Schwartz talking about some kind of U5 description of RNS, which sounds like it has a similar flavor to what I'm discussing here. But again, I haven't been able to understand these papers, but it does have a similar flavor. So maybe you could try to study this directly in RNS also by seeing what it means when the space-time, when the amplitude computation preserves a subset of the space-time supersymmetry. So why that somehow helps.
Can I ask you another question about the intuitive understanding of this formalism that you described? So you call it a modified RNS formalism because you add these auxiliary variables somehow, right? Additional variables in the RNS formalism. You somehow you modify the BRST operators so that they don't contribute.
That's right.
And then you show that there is a different twist you can make so that you recover your spinor formalism.
That's right.
Is there, I mean, can you describe the way back, some way, let's say from the pure spinor formalism back to this modified RNS formalism?
Yeah. So to go back to the RNS formalism, you need to obviously introduce some new variables. So
start from the pure spinor formalism.
Let's suppose we start here. So here's the pure spinor formalism just starts with this lambda alpha d alpha here, just this term here. That was the pure spinor formalism. Now we're going to introduce, so the RNS formalism, of course, has some BC ghosts, right? And beta gamma ghosts. We're going to have to add this topological set. And so instead of adding the theta lambda, now we're going to add these topological variables. So these are the original variables. And now we're going to add these auxiliary variables, which maybe you can think of as allowing the world sheet supersymmetry to be manifest. So in the opposite case, we wanted to make space-time supersymmetry manifest. Here, in some sense, you want to make the world sheet supersymmetry manifest. So you can think of it in that way. I haven't thought about it yet, but maybe you could think of starting with pure spinor and then seeing what you need in order to make the world sheet supersymmetry manifest. And maybe that would land you on the RNS formalism. So I guess, yeah, you'd have to just do the opposite twisting and try to construct these n equals 1 superconformal generators.
You don't have any picture chaining operators in the modified RNS?
So, sorry, so in the, so when you compute hyogenous amplitudes in RNS, yes, you need to introduce picture changing operators in order to get essentially the correct picture for the hyogenous scattering. Now, I didn't mention in the pure spinor formalism, what you have to introduce is this B ghost to compute higher loop amplitudes. And the B ghost, I think I wrote it down here somewhere. So the B ghost is this object here. I guess I didn't write it explicitly. It has these terms here which look very much like picture changing operators. So the picture changing operator in RNS was something like e to the phi psi m dxm. And this object here, if you write it in terms of the untwisted variables, pi is essentially like dx, and lambda bar gamma d is essentially like this e to the phi psi. So it does have a similar flavor. The B ghosts in the RNS form, in the pure spinor formalism, and the picture raising operators in RNS. So that's, of course, going to be necessary if we're going to have to relate the higher genus surfaces, higher genus amplitudes. I don't know if that was that your question about how picture raising comes in?
Yeah. Yeah, thanks.
Any other question?
Can you imagine, I don't know if that makes any sense, but imagine applications in sort of string field theory or for tachyon condensation or something like this? I mean, does this?
So yeah, tachyon condensation. So tachyons are much easier to describe using the RNS formalism. So if you want to describe tachyons in Ramond backgrounds, for example, there's a problem in any formalism. So in RNS, of course, the problem is to describe the Ramond background. In the pure spinor formalism, the problem is to describe the tachyon. So I think describing tachyons in Ramond backgrounds is maybe impossible to do. So tachyon condensation, I would say, no, that's probably RNS. You don't want to do pure spinors. But you can, of course, do other things with superstring field theory. So you could describe, for example, instanton solutions or things like that, where space-time supersymmetry is useful. So string field theory in pure spinor formalism has some difficulties, mainly because of the pure spinors. So it's not, well, it's not difficult to describe the classical string field theory action, which is actually, Martin spoke a little bit about it. So you can write down an action of something like phi cube phi plus phi cube using the pure spinor field, using the pure spinor formalism. But if you want to quantize or gauge fix even, you need to describe something like this B ghost. And as I mentioned, the B ghost has these poles in lambda lambda bar, and that immediately starts to cause problems just because once you allow poles in lambda lambda bar, you have to decide how divergent the states can be in these poles.
I think it's even more complicated, Nathan, because it's not enough to have the B ghost. You need to do a full BV, consistent BV gauge fixing, which I don't know how to do yet.
Okay. So yeah, so I think we agree. So gauge fixing is complicated. It's not known how to do gauge fixing using the string field theory, but it's an interesting question.
Any further question? So if there are no further questions, I thank again the speaker. And see you in 30 minutes. Thank you very much again.
Why is that?
Can you please share your slide, Richard?
I am trying to pull them up now. One second. Can you see my slides?
Yes, yes. All right, I think we're good to go. So we're very happy to have Richard Eager, who's going to speak about maximally twisted 11-dimensional supergravity.
Thank you very much. So I will be talking about maximally twisted 11-dimensional supergravity. And this is based on joint work with Fabian Honor and work of other people as well for different sections. So the main motivation is to understand twisted supergravity, and a very inspirational quote by Kevin Costello and Natalie Paquette is that high energy theory and mathematics engage in a rich exchange of ideas from which the ADS-CFT correspondence has so far largely abstained. And part of the goal of this talk is to have this rich exchange of ideas between high energy theory and mathematics. And I think this conference is bringing people together from both math and physics, and I hope to kind of promote this exchange. So one of the key motivations for twisting, which is part of this conference, actually goes back to four-dimensional supersymmetric quantum field theory, and in particular, the relationship between the topological twist of 40n equals 2 super Yang-Mills, which is related to Donaldson theory. So Donaldson's study of the moduli space of instantons in Yang-Mills theory led to remarkable results in the study of differentiable four manifolds. And a careful analysis of the singularities in the moduli space of instantons actually led to the discovery of an exotic differentiable structure on R4. So prompted by Atiyah, Witten introduced topological twists and showed that the Donaldson and Floer's theories could be described by a topological twist of 40n equals 2 supersymmetric Yang-Mills theory with gauge group SU2. And then, so that's kind of connection to mathematics. And then on the physics side, Seiberg and Witten described the low energy effective dynamics of 40n equals 2 supersymmetric Yang-Mills theory with gauge group SU2 in terms of an effective theory with gauge group U1 coupled to a magnetic monopole. So Seiberg-Witten invariants were easier to compute than Donaldson's invariants and led to further dramatic progress in the geometry of four manifolds. Similarly, twists of 60 supersymmetric Yang-Mills led to Donaldson theory and results for the enumerative geometry of Claviau manifolds. So a nice quote is that the physicists keep coming up with amazing equations for us to solve, us being mathematicians. Once we know the equations, we can get lots of mathematics out of them, but why can't we find the equations ourselves? So part of this talk might be considered a cookbook for mathematicians to come up with beautiful equations in mathematical physics coming from the pure spinor formalism. And while twisting had been very broadly successful for supersymmetric gauge theories, for twisted supergravity, a couple new innovations needed to be made. And the primary one I want to focus on is Costello and Lee's generalization of Witten's notion of a topological twist to holomorphic twists of supergravity and partial topological twists. And so their construction elegantly modifies the differential of the theory under consideration by taking their BV complex and adding a nilpotent supercharge, where BV is going to be the Bettelin-Vilkovitsky complex. And to follow their recipe, we need to construct BV complexes for supergravity and choose a nilpotent supercharge. And rather surprisingly, both of these problems can be addressed using nilpotence varieties, which generalize the pure spinor superfield technique. So there's a very basic outline. we're going to define nilpotence varieties following work with Johannes Walscher and Ingmar Sabiri, and then kind of lightning review of supersymmetry in the VB formalism. And then we're going to generalize the pure spinor formalism to construct multiplets from equivariant modules over nilpotence varieties. And this is joint with Fabian Hahner, Ingmar Sabiri, and Brian Williams. And this work is actually yet to appear. So it's going to be a little preview of that. And then we're going to follow Costello and Lee's procedure to twist 11-dimensional supergravity, which was joint with Fabian. Okay, so our first topic is going to be nilpotence varieties, and we can associate them to any supersymmetry algebra. And they have two primary uses that kind of combine both of the themes of this conference, which the nilpotence varieties parameterize all possible topological and partial topological twists of the supersymmetry algebra. And they can also be used to construct superfields and off-shell representations of the extended supersymmetry algebra. So maybe some familiar examples is the 10D n equals 1 supersymmetry algebra has a nilpotence variety, which is Berkovits space of pure spinors. And I'm always going to look at the projectivized nilpotence variety. And so this is actually equivalent to the orthogonal Grassmannian 510, which is a subset of the Grassmannian 510 of complex 5 planes in C10. And then there's going to be an additional restriction on which 5 planes are allowed, given by an orthogonality constraint. And a simpler example would be n equals 1 supersymmetry in 60, the nilpotence variety. So again, these are minimal supersymmetries, so they're just spaces of what we call Berkovits pure spinors. So here the nilpotence variety would be P3 times P1. And in 40, the nilpotence variety is a disjoint union of two P1s. So a new example was actually defined in Martin's talk. So you can act, and it's a very nice toy example which illuminates many properties of nilpotence varieties and multiplets, is you take the supercharges Q to be 2 forms on C5, and kind of the generalized momentum to be 4 forms on C5, and the super bracket is just going to be the wedge product of the 2 forms, which will give you a 4 form. And then it's kind of a fun exercise to see that the nilpotence variety is the Grassmannian 2-5. And what I like about these nilpotence varieties is they show some very interesting connection to mathematics. And in particular, they are the only 2 Hartshorne varieties among rational homogeneous spaces. And it seems kind of like an odd coincidence that 2 of the most popular supersymmetry algebras have kind of a fundamental role in algebraic geometry. And the motivation for Hartshorne varieties is actually somewhat closely connected to the idea of twisting. So a Hartshorne variety is defined to be a smooth variety in Pn of dimension 2/3 n, which is not a complete intersection. And Hartshorne's conjecture predicts that this little n greater than 2/3 n is impossible. So it's about trying to be homogeneous spaces that are of large codimension and projective space. And it's actually quite difficult to do. And sort of the extremal examples of this are the space of 10-dimensional pure spinors in this Grassmannian 2-5. And a fun quote from Hartshorne is that while he's not convinced of the truth of the statement, he thinks it's kind of useful to have this particular problem in mind. So,
Richard, by impossible,
yes.
By impossible, you mean larger dimension is a complete intersection? Is that what's impossible?
Well, so you can have complete intersections in any. Sorry, can you repeat the question?
What's Hartshone's conjecture? It says that n is greater than 2/3, but
if you're that it's impossible to have a non-complete intersection of higher codimension.
Okay, thanks.
Yeah, so kind of easy examples are like Grassmannians. So if you take larger Grassmannians, like Grassmannian, yeah, so let's see. So Grassmannian 2.5, right, is in P9 and it's dimension 4. Yeah, so this is so it's dimension 4, which means it's codimension 6. So that's kind of a maximal codimension you can have. For example, you couldn't have anything of codimension 7. Yeah, so I should say this little n is the related to codimension.
So the Grassmannian 2.5 is dimension 6, I think.
Sorry, yes, it's Grassmannian 2.5 is dimension 6.
2/3 of 9.
Which is 2/3 of 9, yeah. So this is the extremality.
OGR is more complicated because the dimension is, but it's thin.
Yeah, so this is kind of an aside, but it's related to the fact that complete intersections actually have a natural multiplet, which is related to being a topological twist. And somehow these Hartshorne varieties are as far as possible from having topological twists. And kind of as you get further away from being a complete intersection, you have more interesting representation theory of supermultiplets. Okay, but yeah, so it's a really fun aside, and I liked putting this up because somehow these two natural examples that physicists were stumbled upon are kind of related to somewhat deep conjecture in algebraic geometry. Okay, so I wanted to move on to the twist from nilpotence varieties. And so nilpotence varieties are actually stratified varieties, and the different strata correspond to different twists. And there's two main ways new strata can arise. One is from the fact that the nilpotence variety can be singular, and a singular locus is an interesting stratum. And then you can also have intersections of different components. And so I'll try to illustrate this with some examples. Kind of the most dramatic one, or one of the more dramatic ones, is the 5D n equals 2 nilpotence variety. And so it's actually a complete intersection of 5 quadrics in P15, and it's of degree 32, coming from the fact that there are 5 quadrics. So the degree is just kind of counting of intersection numbers. So each time you have a quadric, right, you take 2 to the 5th and get the 32 for the degree. If you kept on intersecting with hyperplanes, you would actually get 32 points if they're in generic position. And the interesting thing about this nilpotence variety is it's a disjoint union of 2 other nilpotence varieties, which from physics, maybe it's not too surprising. They're the 10D n equals 1 nilpotence variety and the 6D n equals 2 nilpotence variety. And so these also have a kind of interesting geometric interpretation of being linked in the sense of liaison theory. And a simple consequence is actually that the degrees of these algebraic varieties are additive. So this pure spinor variety is degree 12, and the 2D 6D n equals 2 variety is degree 20. And so they add up to 32. And you can actually translate representation theory of multiplets on any 2 varieties that are linked in terms of each other. So it's a little surprising that representation theory of the 10D n equals 1 algebra gives you certain results about the representation theory of the 6D n equals 2 supersymmetry algebra. And then there's a sketch of the stratification below. And so it's kind of, here are these 2 components, and they intersect over some kind of very complicated locus. And then this complicated locus is kind of some singular variety, and it has a singular locus, which is P3 times P3. So this singular locus corresponds to the holomorphic twist. And here, these 2 top strata are topological twists, correspond to distinct topological twists. And in between, you have a mixed, a partial topological twist. So some further examples that are going to be relevant for the later part of the talk is in 11 dimensions, the nilpotence variety is 22-dimensional, and its singular locus is the smooth variety, the orthogonal Grassmannian 511, which is the same as the orthogonal Grassmannian 612. And so on the singular locus, the unbroken symmetry algebra is U5, and it leads to the holomorphic, well, it's holomorphic in, say, 5 complex dimensions and topological in 1. So it's this holomorphic twist studied by Barry Williams, and I hope Brian will be talking about this in his talk later this week. And the stabilizer of a generic point, so this is kind of off the singular locus, is a parabolic subgroup with Levy factor G2 times GL2. And in physical language, so generic point is a spinor, and the spinor is going to correspond to a mixed twist that's holomorphic for the 40 n equals 1 and topological on G2. And so these have been studied in M-theory compactifications for a very long time. And the idea is to actually, in terms of computing things like corrections to F terms coming from G2 compactifications of M-theory, but we want to study them from the slightly different perspective of mixed topological twists. So kind of the motivation came from several conjectures of Costello, and we worked with Fabian. We derived parts of Costello's conjecture. Okay, so kind of going back to this recipe of Costello-Lee, first you need to pick a nilpotent supercharge. And so our nilpotent, so we discussed how we're going to use the nilpotence variety to pick a point that's on the generic locus, which defines the maximal topological twist. And then the second point of the nilpotence variety is to use it to construct multiplets. And so we want to construct a multiplet for 11-dimensional supergravity, and then follow the Costello-Lee procedure to twist. And the key ingredient is actually constructing what we call BV multiplets, because in extended supersymmetry algebras, you don't necessarily have complete off-shell representations unless you pass to the BV formalism. And just a general motivation for the BV formalism is that many important equations of mathematical physics arise from the critical locus of a degenerate action functional S on a space of fields equipped with some gauge symmetry G. And the BV formalism handles degeneracies by replacing the critical locus with the derived critical locus. And this is often handled in the physics literature by adding what are called the anti-fields, which is the key part of the BV formalism. And the derived critical locus comes equipped with an odd shifted symplectic structure, which is the anti-bracket. And gauge fixing in the BV formalism is achieved by choosing a Lagrangian submanifold in the space of BV fields. And the space of BV fields usually arises as sections of a graded vector bundle over the space-time, where the differential D is a differential operator. And so normally we call the Z grading the ghost number, and the Z mod 2Z grading the parity, which distinguishes bosons and fermions. Okay. So in this part, I want to explain how we use a generalization of the Berkovits and Siderall pure spinor formalism to describe supersymmetry multiplets as modules over nilpotence varieties. And it is similar in spirit to the Borel-Weber construction of representations in terms of the cohomology of line bundles. And maybe in physics, the most familiar example of this Borel-Weber construction is that the spin J representations of SU2 can be realized as sections of line bundles over CP1. And the idea that we got from work of Martin Siderall is that we just need to kind of a key input of describing multiplets is to give a free presentation of modules. And so this ring is always going to be correspond to a nilpotence variety, but I'm just going to set this up quite generally. So a module M over any ring S can be described using a free presentation, which is just an exact sequence where F0 and F1 are free modules, and the relations are encoded by the map phi. And a module M can then be described as the co-kernel of the map phi. And the kind of key input is going to be viewing phi as a matrix, which give relations to obtain M as a quotient from F0. And just taking this definition of the co-kernel, so we're always going to describe modules as co-kernels, but just writing out what it means to quotient, it just means that an element of of M can be viewed as an element F0, little F0 of this module, free module, up to a shift of anything that's in the image of phi. And so this is what Martin Sederwall calls shift symmetry, and it's very useful for constructing modules if you can find this type of presentation. And so for each equivariant module over a nilpotence variety, this work kind of constructs a general machine that will spit out representations of supersymmetry algebras. And I want to go through that in a simple example. And the first step of this procedure is you extend the free presentation of M to a free resolution by successively taking kernels. And it's kind of a classic theorem of Hilbert that these resolutions are actually finite. So before moving to 11-dimensional supergravity, I wanted to kind of illustrate this technique in 6D in a very clean example, which highlights the necessity of using the BV formalism and this kind of generalized pure spinor superfield technique. So in 6 dimensions, recall that the nilpotence variety, or the supersymmetry algebra, takes the following form, where you just have the anti-commutator. Also, the Q's are actually in the spinor representation, but they also have an R symmetry index I. And we have this super bracket. And this immediately leads to 6 quadratic equations, which describes the nilpotence variety as basically the vanishing locus of a 4x2 matrix, which is this matrix phi. And there's kind of so the minors, so these 6 equations you can actually view as the 2x2 minors of this matrix phi. And that's what's called a determinantal variety, and its projectivization is P3 times P1, which is the nilpotence variety. And this matrix phi actually can be used as the map for a free presentation of a module. And kind of naturally, just by looking at co-kernel phi, defines a module over the affine cone of P3 times P1. And if you push that down to the projectivization, this module, co-kernel phi, is the line bundle kind of O, 1 on P3 times P1. So it's just functions on P3 tensored with sections of a line bundle O1 over P1. And the component fields of the hypermultiplet are recovered by the minimal free resolution of the module gamma. So just to work through that, the minimal free resolution of gamma in R modules takes the following form, and it's a special case of the Buxbaum rim complex. And so here, this C2 is actually this R symmetry space. I decide not to give it a name. And then the S plus is the spinor representation. So we can read off. So this phi actually is going to be an R symmetry doublet. So it's a scalar. And then this S plus is going to be a fermion psi. And this, we can actually identify the wedge cube of S plus with the antifield of psi. And then finally, this last term is the wedge 4 is going to be a singlet. So it's going to be an R symmetry doublet and a scalar, which is the antifield of the first scalar. And so in particular, from the structure of the resolution, we see that it's necessary not only to have the scalar and the fermion, but we must necessarily include their antifields. And this is special to having extended supersymmetry. And we can go further. So I want to go through the procedure of basically breaking down so this is the pure spinor formalism where we take the differential and separate it into two pieces. And the first piece governs the minimal free resolution. And then the second piece is kind of a correction. And anyway, this kind of work in progress with Ingmar, Fabian, and Brian. They'll go through this in detail, but it's very similar to kind of the work in Berkovits papers. And we can find representatives for what we call D-naught cohomology for all the fields, which is, and so they have a theta and lambda degree, maybe familiar from pure spinor formalism. And then from this, we can read off the non-derivative supersymmetry transformations. And kind of the key point for here is that there's a very interesting transformation that relates the supersymmetry variation of a fermion to that of its antifield. And this is related to the fact that the supersymmetry algebra only closes up to the equations of motion. And in particular, we recover the fact that this fermion satisfies the Dirac equation, the scalar satisfies the Klein-Gordon equation. Okay, so this is kind of a new example. I should say that the supersymmetry in the BV formalism in this particular example of the 60n equals 1 hypermultiplet was worked out in a very beautiful paper by Laurent Beaulieu and his collaborators back in the early 80s. And it was kind of nice to rederive their results using this generalization of the pure spinor formalism. Okay, so the idea is we want to take this machine and apply it now. So this is the machine that produces BV multiplets. And once we have the BV multiplet, we're going to twist it. And so the twisting of Castelli just works by taking invariants of a nilpotent fermionic symmetry Q, and the invariants are then the cohomology of that operator. So the relevant differential acting on operators of the gauge theory will be of the form S plus Q, where S is the original BV operator and Q is the nilpotent supercharge. And we just add them to get the new BV differential. So kind of the goal of the latter half of this talk is to derive Castello's conjecture for the partial topological twist of 11-dimensional supergravity on manifolds M7 times M4 of G2 times SU2 holonomy. And so as a free BV theory, the twisted theory is described by a cochain complex, which is just the tensor product of de Rham differential forms on M7, tensored with the Dolbeau anti-holomorphic forms on M4, with a twisted differential, which is just the sum of the de Rham differential on M7 and the del bar operator on M4. And kind of very importantly, there will be higher interaction terms. And one of the main ideas is to use Sederwall's description of 11-dimensional supergravity in the pure spinor formalism to try to drive Costello's full conjecture. But for today, we're just going to look at deriving this field content for the free non-interacting theory. Or sorry, for the where we disregard the higher interaction terms. Okay, so when we run kind of the pure spinor formalism, we get a very beautiful BV multiplet for 11-dimensional supergravity, and it contains a, well, the fields are in this theta degree. Sorry. So the fields we have in lambda degree 3, which are going to be a gauge 3 form, a graviton, and a Rita-Schwinger field. And the graviton has a vector ghost. The Rita-Schwinger field has a spinor ghost. And then the 3 form has a system of ghosts for ghosts, including a 2-form ghost, and then a 1-form ghost for ghost, and then a scalar, which is, I guess, ghost for ghost for ghost. And in particular, we also get all of the corresponding anti-fields for these fields just by resolving the structure sheaf of the 11-dimensional nilpotence variety. And the interesting thing is, just like in the hypermultiplet for 16 equals 1, there's going to be a nonlinear supersymmetry transformation connecting the Rita-Schwinger field and its anti-field, and it will necessarily be on shell and satisfy the Rita-Schwinger equation. So using the ideas of homotopy transfer that are in this work to appear, we can either derive or actually use this older work of Berkovits to get the non-derivative supersymmetry transformations of all the operators in 11-dimensional supergravity. And kind of a very interesting thing is that many of the terms are nonlinear in the supersymmetry parameter epsilon. So for example, this variation is quadratic, and then these are all quadratic. And maybe the more familiar supersymmetry transformations, like for the physical fields, or for the bosonic physical fields of the 3-form and the graviton, are just linear in the supersymmetry parameter. But even for the Rita-Schwinger field, there's a nonlinear supersymmetry transformation connecting it to its anti-field. So the strategy is kind of quite straightforward. What we want to do is take the field content and the supersymmetry transformations and decompose them under the G2 times SU2 times U1 symmetry, and then modify the transformation rules by our nilpotent spinor. So the spinor representation in 11 dimensions decomposes as a tensor product of a 7-dimensional and 4-dimensional spinor representations. And we can further write them out in terms of a Lagrangian subspace in 4 dimensions. And so similarly, so that's the decomposition of the 4D spinor, but on a manifold M7 with G2 holonomy, the 7-dimensional spinor representation decomposes further as a singlet under G2 and a vector representation of G2. And so we can just describe or decompose the 11-dimensional spinor that we're going to twist by as sorry, so this is going to be the entire 11-dimensional spinner as this contribution from 70 and this contribution from 40. Right, and then when we twist, we're going to just pick out a particular component, which is going to be a singlet of the G2 and also a singlet under the SU2. Right, so this is going to be the particular supercharge we twist by. And so we immediately see that this supercharge Q is invariant under the action of G2 times SU2 minus, and it has U1 L charge minus 1. And so kind of the first thing we'd want to do is write out the supersymmetry transformations in terms of this decomposition. And kind of beautifully, the normal space to the nilpotence variety is spanned by these supercharges, and they satisfy these anti-commutator relations. But the anti-commutator of Q with the Q alpha is 0, which is related to the fact that we have a holomorphic twist on the 4-dimensional manifold of holonomy SU2. Okay, so we have the decomposition of the supercharge, and so this is the charge we twist by. So we want to decompose all the fields, and we furthermore want to decompose all the gamma matrices because they appear in the supersymmetry transformations. And maybe just to remind you, the symmetric square of the 11-dimensional spinor representation decomposes as a direct sum of 3 irreducible representations. And we get projections onto all 3 factors, which are the gamma matrices. And essentially, so interesting thing, of course, is that we have wedge 2 and wedge 5, which correspond to the possible central extensions of the supersymmetry algebra, giving sources for M2 and M5 branes. And the important thing is we just decompose everything in sight. So we decompose the symmetric square and these vector and these wedge products of the 11-dimensional fundamental representation. And that essentially constrains all the gamma matrices up to scalars by Schur's theorem. And so that was kind of the level of detail which a lot of these computations go through. In principle, we could use computer algebra to nail down all the constants, but for the most part, we don't need the precise constants in the decomposition of the gamma matrices. So kind of an example of this, of how the computation goes, I'm not going to go into all the gory details, is we just take a simple field like the diffeomorphism ghost, and it's a vector, so it decomposes into a 7-dimensional vector on G2, and then it's a holomorphic, well, it's kind of related to holomorphic and anti-holomorphic components on R4. And we want to decompose the supersymmetry transformation that takes the vector ghost into the spinor ghost. And we see that 2 components of the spinor ghost are in the image, but 1 component is not. And so these two transformations are going to lead to cancellations in the twisted theory. And so these components will actually not survive, we say not survive the twist. This component is quite interesting. In a sense, it's not going to be in the twist of the BV multiple that I showed you, but it's actually going to be the leading component for a non-trivial module over the 11-dimensional nilpotence variety. Right, so this is just summarizing what I said. And then what we want to do is take all of the field contents and kind of in the paper, so this is coming from our paper, where each arrow shows a cancellation. So for example, this cancellation of the components of the vector ghost. So they're labeled by A, and so this component cancels with part of the ghost for ghost in C1. And so anytime there's a supersymmetry transformation leading to a cancellation, you just cross out those fields, and the remaining fields are all circled in blue. And of course, this is just half of the component fields, and they're going to be similarly the anti-fields as well. And essentially, this summarizes all the main computations of the paper. And the remarkable thing is, after you decompose all the supersymmetry transformations and take into account all the cancellations, the circle fields in blue precisely organize into this tensor product of Durham forms on M7 and Bilbao forms on M4, or these anti-holomorphic forms on M4. And so you can kind of go back and see, in fact, that only parts of the three-form ghost system survived, and that parts of the Rarita-Schwinger field survived, and their anti-fields. So in particular, for this multiplet, the graviton did not survive, but as I mentioned, there's going to be one other multiplet that will play a role in when we turn back on higher order interactions. And the leading component in that multiplet should actually be this holomorphic piece of the graviton ghost. Okay, so then going back to the main motivation of the introduction, one of the main applications that we're looking forward to is applying this to twisted holography, which was the main motivation of Costello and Lee. And then there's already been several works that have just assumed this conjecture of Costello and Lee, or further conjectures by Costello, and kind of proceeded from there using lots of interesting homological algebra. But the idea is that once we get this bridge fully up and running, any result that's in this twisted holography program will be an actual derivation of a physical result. And one of my maybe personal motivations for why I was interested in twisted holography is that superconformal indices are kind of natural examples of invariance that you compute in holomorphically twisted theories. And so with Johannes Schmidt, we computed the superconformal index of ADS4 times a generic Sasaki-Einstein 7-manifold in terms of holomorphic data for the Calabi-Yau cone over the Sasaki-Einstein. And I've been informed that Costello and Raghav Andran are actually rederiving these results directly in twisted holography. And you can also consider superconformal index of ADS7 times S4. And another kind of beautiful application of the twisted M theory is you can couple it, especially the G2 factor, to a partial topological twist of 70 Yang-Mills and consider a G2 analog of Donaldson-Thomas theory and BCOV theory, which is already a published work of O, Del Zotto, and Zhao. And yeah, maybe before I finish, I should say there's also older work of myself, Johannes Schmidt, and Yuji Tachikawa, where we considered the superconformal index of ADS5 times Sasaki-Einstein 5-manifold and related the local operators to cyclic homology of that theory. And then very recently, there's work of Nikolai Babev and collaborators, Malik, Robinson, Semplebin, and Van Whedon, who derived the Klutzeklein spectroscopy for the Ley-Strassler superconformal field theory, and expressed that, and the results actually match computations of the cyclic homology of Michael Vandenberg. So these were field theory computations that with Johanna Shmuda and Yuji Tachikawa that derive cyclic homology. They gave local operators in terms of cyclic homology, and then they kind of maybe 8 years later, this gravity group could rederive them using EDA-CFT. But the hope is that actually using twisted holography, you can get a much cleaner derivation of all these Klutzeklein spectra and come close to giving a mathematical proof of ADS-CFT along a slightly different lines than Nathan Berkovitz's proposal. Okay, so thank you very much for listening. I know it's a little fast, but also sticking to the original.
Any question for the speaker? Please.
Could you say something, thank you for a nice talk. Could you say something about how you're planning to derive interactions?
Okay, right, so there is an older, so there's a very beautiful paper that maybe the main point of this talk should have been just to emphasize that there's a work by Martin Setterwall. It's something like manifestly supersymmetric 11-dimensional supergravity. And the main, and it gave an action for 11-dimensional supergravity in the pure spinor formalism. And a key part of that is he had constructed the action using certain differential operators. And so the idea is that these differential operators should be considered as some differential operators between well, various sheaves on the nilpotent variety. And the hope is actually that by studying these equivariant modules, we can not only, well, we can use the geometry to construct interactions. So one part I didn't say is that all these varieties have natural volume forms, and they have, if you have multiplets that pair, right, sometimes you can just directly pair to the volume form. That naturally gives you a way of producing interactions. And so part of it would just be trying to understand, first of all, the classification of multiplets. And for 11-dimensional supergravity, there's a very beautiful multiplet that comes from Chevalley-Eilenberg cohomology of super translations. And it seems like this multiplet starts with, well, it contains the holomorphic piece of the graviton ghost, and it also will contain a little piece of the graviton on R4, and that the Chevalley-Eilenberg cohomology gives you it's actually a rank 2 module over the nilpotent variety. And our hope is to kind of relate this module coming from Chevalley-Eilenberg cohomology to the differential operators in Martin Setterwall's work, and to use that to write down both the full BV action and then be able to twist the interactions. And as far as I can tell, maybe Martin can correct me, that the full expansion of the BV action for 11-dimensional supergravity has never fully been worked out. So it's kind of a beautiful open problem. And kind of, there's actually a reverse idea that I learned from Value Kano Singer is that sometimes there's a two-way street, and there's a procedure called untwisting where you do all, if you have a twisted theory and you do all the gauge fixing for it, all the terms you introduce by gauge fixing sometimes reproduces the untwisted theory. And so perhaps a different avenue is just by starting with this conjecture of Costello, and Costello, I should say, also conjectured the form of the twisted interactions, that you could try to untwist that theory and learn something about the full BB form of 11-dimensional supergravity.
Thank you. Other question?
Can you say some more about the Chevalier-Eilenberg cohomology? Like what co-cycles are of interest?
Okay, so Chevalier-Eilenberg cohomology plays several interesting roles. So one, right, when they're singlet co-cycles, there's some sort of Serre spectral sequence that lets you extend the algebra. It's actually very interesting in terms of there's this Doria-Frey approach to twisted supergravity, and they have a whole something like on the NLab, which is like this M-theory Lie-3 algebra or even M-theory Lie-6 algebra that should describe the ghost action of twisted 11-dimensional supergravity. And that's all governed by kind of singlets in Chevalier-Eilenberg cohomology. There's another thing you can do with the Chevalier-Eilenberg cohomology is you just compute Chevalier-Eilenberg cohomology of super translations. And instead of looking at the graded pieces of Chevalier-Eilenberg cohomology, you can consider that cohomology group as a module over the nilpotence variety. And these modules give you an input to run this generalized pure spinor formalism and construct non-trivial modules, just like we constructed the 6D hypermultiplet from a non-trivial module. So that's the second application of Chevalier-Eilenberg cohomology. And I should say, I'm not sure that where exactly it's written down. Of course, there's a lot of work by Movshev and Schwartz and collaborators, but for 11-dimensional super translations, there's actually only 3 non-trivial Chevalier-Eilenberg cohomology groups. And in particular, they're of ranks 1, 2, and 1. And the top Chevalier-Eilenberg cohomology is like a shift of the 0th Chevalier-Eilenberg cohomology. And you can start imagining things like taking the second wedge power of the first Chevalier-Eilenberg cohomology, and that gives you a map to the second Chevalier-Eilenberg cohomology. And so using the second Chevalier-Eilenberg cohomology is very similar to a volume form on the nilpotence variety. And so this kind of gives you a hint of how you can understand pure spinor actions geometrically.
So Richard, maybe you mean like with respect to a particular totalization of the degree, right? Because I think this cohomology is going to be of infinite rank over the field, but it's going to be like a finite rank as a module over this ring, which ends up in degree 0 after you totalize.
Yeah, it's a rank of the, yeah, so that's what I was trying to make the distinction, where in a lot of literature, people think the Chevalier-Eilenberg cohomology as a graded vector space, and it has an infinite number of graded pieces. And you're right to give this warning, but if you consider it as a module over the nilpotence variety, that module will have finite rank. And I should say that sort of looking at this infinite, looking at Chevalier-Eilenberg cohomology as an infinite dimensional graded vector space is kind of primarily how it appears in the literature. And we're hoping that viewing it as a module it has more geometric structure, and we can kind of extract a little more mileage from it this way.
Actually, we have a paper with Simone Snoia and other people about Chevalier-Island homology for superalgebra, super translations, actually, where we show indeed how you get a finite model, so where it comes from. So it is a whole structure in it. I mean, it's very clear what happened. You don't know it.
Yeah, okay. Yeah, so it has appeared in several places, but I just want to emphasize that this is a very useful approach to Chevalier-Eilenberg cohomology. Maybe the last thing I should say is there's very surprising things, and maybe for mathematicians or even physicists, I think there was a paper of Howe and Berkovits where they consider, so for example, Chevalier-Eilenberg cohomology of 10D n equals 1 supertranslations has a very beautiful structure. The first Chevalier-Eilenberg cohomology group, roughly speaking, has rank 5. And you can approximately view the higher Chevalier-Eilenberg cohomology groups as the exterior powers of this rank 5 module. But it's not quite true on the nose. And it's related to the fact that, not all these, that there's certain kind of exceptional cohomology groups coming from Borel-Weybot that we don't fully understand yet. And we had a list of trying to understand these Chevalier-Eilenberg cohomology groups, like Chevalier-Eilenberg, the second Chevalier-Eilenberg cohomology group is supposed to be related to the current multiplet for 10D n equals 1 supersymmetry. And so if you have results on Chevalier-Eilenberg cohomology groups that can compute them, it'd be very useful for constructing multiplets.
Other question? So earlier on you said that this variety have canonical volume forms, right? So
yes.
What do you mean by that? Like they are, say, they have a trivial canonical sheaf?
Not all of them. So for example, P3 times P1 has a non-trivial canonical sheaf.
Well, yes, of course, it's a Fano manifold.
Right. So yeah, what I mean is that even
Indeed,
so we write everything in terms of, sometimes it's easier to talk in terms of the cone and to look at the dualizing module. And so in certain cases, like 10D n equals 1, there's a very beautiful like bundle, which is something like 08, or I think either O plus or minus 8 over the orthogonal Grassmannian 510. And the total space of the bundle is Claviau, so you have kind of a natural Claviau volume form on the cone over. So the cone over space of 10-dimensional pure spinors is Claviau, but in general, like 6D n equals 1 is only going to be a Cohn-Macaulay ring. And so there is, but still you can use the duality theory to cook up certain pairings in these other cases. But I admit the best situation is when the nilpotence variety, the total space of the nilpotence variety is Claviau, or some sort of singular Claviau, which is known as Gorenstein.
Okay, so you use some kind of a local Claviau structure or something. Yeah,
so there's both the nilpotence variety and there's an affine nilpotence variety, and then its projectivization. And the affine nilpotence variety has this singular Claviau structure known as Gorenstein. In certain cases, like 10D n equals 1, but in other cases, it's not Claviau or not even Gorenstein. So it really depends on the algebra in question, and it's related to the types of interactions you can construct.
Okay, thank you. Other question? there are no further questions, I will thank the speaker again. Thank you very much. Hi, Thomas. Can you try to share the screen?
Yes, I want just testing my sound. Can you hear me first?
Yeah, we can hear you very well.
Okay, great. I'll try to share the screen. Okay, 1 second. This is currently not working. Let me try one more time. Okay, can you see that?
Yes. All right.
Okay, great.
So we're good to go?
1 second. I need to organize my windows here a little bit so I can see my actual slides. What's your preferred way of doing questions? I'm sort of happy for people to just shout, and that's what's been happening so far.
That will work.
More or less.
That will work here. Can you hear me?
Yeah, I can hear you.
Yeah, so that's how you're going to hear questions.
Fantastic.
I don't know if you can see somebody raising their hand here in the room.
With effort, shouting is better.
Okay.
Okay. Good. All right, I'm good to go.
Okay, so it's a pleasure to have Thomas Dumitrescu, who's going to speak about two-group global symmetry in 6 dimensions. Thank you very much.
Okay, thanks. Thank you so much for the invitation. It's really a pleasure to finally join you after such a long time of anticipation. And virtually is better than not at all. So thanks for the invitation to speak. I'm going to be talking about a two-group global symmetries in quantum field theory. I'll explain what these are. And concretely, I'm going to do that in the context of 6-dimensional quantum field theories, mostly supersymmetric theories inspired by string theory. So this is based on a paper that I wrote last year with Clay Cordova and Ken Trilligator, as well as some previous work and some ongoing work that I may or may not have time to mention. So since I decided to focus on 60 theories, let me give you a little bit of context. I'm sure very familiar to many of you. It's a famous story that if you decouple gravity in various string or brane constructions, you can construct many examples of interacting UV-complete theories in 6 dimensions that are not gravitational, that do not have dynamical gravity. And all the known controlled examples preserve some amount of supersymmetry for various reasons that comes only in 3 different forms. There's the minimal supersymmetric 1, 0 theories, and then there's the 2, 0 and 1, 1 theories. 60 supersymmetry is chiral, so this refers to the chirality of the 60 spinors. Okay, so this is a long and famous and beautiful story that I'll not review in detail, and I'll also omit many references, so I apologize for that. Now, when you take such a decoupling limit, depending on how you take it, the non-gravitational theory you get is typically not a local quantum field theory. Instead, generically, what you land on is what's now called a little string theory. So little string theory is characterized by a mass scale, a little string mass scale M string, and only in the deep IR below that mass scale does it flow to a conventional quantum field theory or effective quantum field theory deformed by irrelevant operators. And we can distinguish two scenarios depending a little bit on what this low energy effective field theory looks like at long distances. One option is that the long distance physics is characterized by a superconformal field theory, in other words, by a genuine fixed point of the normalization group, in which case the supersymmetry must necessarily be of type 1, 0 or 2, 0. This is something one can show. And if you wish to study that fixed point on its own, you are entitled to do so. This is a perfectly good quantum field theory. You can forget about the embedding into little string theory. It has well-defined local operators, and in particular, it has a well-defined local and conserved stress tensor, T. And what makes these theories interesting and challenging is that they're typically strongly coupled, and they typically don't have a Lagrangian description. The canonical method for studying such theories is to analyze their moduli space of supersymmetric vacua, in particular in 6 dimensions, the tensor branch of the moduli space, which is the 6D version of the 4-dimensional Coulomb branch. And on the tensor branch, the theory becomes weakly coupled. It flows to a weakly coupled phase and can be analyzed. Okay, so that's option 1. Option 2 is that the infrared field theory itself, even at the origin, might actually be a weakly coupled quantum field theory. It might not be a strongly coupled superconformal theory. For example, it might be a gauge theory in 6 dimensions. If that happens, then the theory there is weakly coupled and even has a Lagrangian, but it is not conformal. As I'll emphasize in a second, 6D gauge theory is not conformal, and it is not UV complete. So in that case, we are not entitled to study this theory in isolation. We must actually remember the embedding into the little string theory and the modifications that kick in at the little string scale. And these are the two different infrared behaviors. Of course, once you go to high enough energy, you really see that the theory is not local. You see the little strings. For example, you see that at high enough energy, the stress tensor stops making sense as a local operator in position space. And you see stringy features like T-duality or a Hagedorn density of states. So I will mostly be interested in the infrared in this talk, but it's good to keep this embedding in mind. And I'll be interested in infrared scenarios of both types, type 1 or type 2, although I'll probably spend more time on type 2 than on type 1. Okay. Now, why am I reviewing this well-known and beautiful story? I'm reviewing it because I would like to re-examine at least a large class of these theories through a different perspective, and that's the perspective of some of their global symmetries, in particular beyond the usual global symmetries that we talk about, like supersymmetry. And that's where the two-group symmetry will make an appearance. And these symmetries will also be closely related to various anomalies in the theory. Okay. So the linchpin for what I'm going to tell you is related to the fact that both type 1 and type 2 theories have infrared phases where they are described by 6-dimensional non-abelian gauge theories. Standard 6D Young-Mills gauge theories. And since we're talking about supersymmetric theories, these sit in some vector multiplets. And as I already said, the 6D gauge coupling is not dimensionless. It has dimension of 1 over energy, and therefore it's irrelevant in the infrared. So 6D gauge theories are IR free. Now, as I said, for strongly coupled superconformal theories, this non-abelian gauge theory description is valid on the tensor branch. But in other examples, like in certain types of little string theories, it's true even at the origin. And what I'm going to say is going to be most dramatic in theories that have such gauge theory phases, although there's a version of it more generally. Now, if you have a 6-dimensional gauge theory, there is an interesting operator that kind of hits you in the face. given the non-abelian 60 gauge field and its field strength little f, you can form the standard instanton density. So the second Chern class of F. This is a closed 4 form, right? Just like the instanton density in 4 dimensions. And therefore its Hodge dual is a conserved 2 form. So I'll call this 2 form J sub instanton, and I'll call it the instanton 2 form. And because it's conserved, it's a current, right? The star of a closed form is always a conserved form. So this J sub I, this instanton density, is a conserved 2 form current in 6 dimensions. And therefore, you can integrate it to make a U1 1 form symmetry in 6 dimensions. And this is a continuous 1 form symmetry because it came from a current, from a local conserved current. And I'll call this the instanton 1 form symmetry. So this symmetry is present in all 60 gauge theories, very similarly to how the monopole symmetry is present in lower dimensional abelian theories. Let me remind you quickly how you get from this conserved 2 form current to the 1 form symmetry. In order to define the corresponding charges, you integrate the instanton density over a 4 cycle, a closed 4 cycle that gives you an integer, gives you the instanton number on that 4 cycle. And there are charged objects whose charge is measured by these kind of integrals. For example, in 60 gauge theories, the uplift of the standard BPST instanton is a solitonic string, and that string is charged under this symmetry. So if you want to count the number of strings, you can integrate that instanton density across the 4-dimensional space transverse to the string, and you'll find the total number of strings. Just like you integrate the magnetic field in lower dimensions in order to count Abrikosov strings in a abelian model. And there are also charged line defects that are operators creating such strings. So this is how continuous 1 form symmetries work in any dimension. Here we're in 6 dimensions. Now, this 1 form symmetry is really a global symmetry. It's not a gauge symmetry. And this is its conserved current. If it is really a conserved current for a global symmetry, it should couple to a background gauge field, a non-dynamical background gauge field. And because this is a 2 form current, that gauge field has to be a B field. So this is by now pretty standard. And so we're going to couple our instanton currents to the B field. And when we write it out in terms of the original instanton density, what we get here is a kind of Green-Schwarz-like term in 6 dimensions that contains the dynamical gauge field little f of my gauge theory and the background B field that I'm using as a source for this current. And it's a standard fact, which is easy to verify here, that current conservation of this 2 form current is equivalent to gauge invariance of the background B field. So if I do a background gauge transformation on big B, then this coupling is conserved. This coupling is invariant. Okay, very good. So this is the sort of general thing I wanted to start with. Now I'm going to start looking at a little string theory example that flows to a weakly coupled gauge theory that has this symmetry. So are there any questions before I move on? Okay. Good. So I'm going to start with the maximally supersymmetric 1,1 little string theory in 6 dimensions. And this is one of the original little string theory examples introduced by Zyberg. And this is easy to visualize as the little string decoupling limit of an NS5 brain stack in type 2B string theory. So here's my NS5 brain stack in 10 dimensions. There's a transverse R4. There are n NS5 brains. The supersymmetry preserved by this setup is 1,1 supersymmetry in 6 dimensions. That's 16 supercharges, same as n equals 4 in 4 dimensions, but non-chiral in 6 dimensions. So I have one left-handed supercharge and one right-handed supercharge in 6D, and there's an SU2 R symmetry acting on each of these doublets. So overall, the R symmetry is SU2 left times SU2 right, which combines to the SO4 or spin 4 that rotates the transverse space here in the brain 7. And in the deep IR, this 1,1 theory flows to 6-dimensional maximally supersymmetric Yang-Mills theory with gauge group UN, where n is the number of NS5 braids. So this is just the 60 version of n equals 4 SUSY Yang-Mills, but here it's an infrared-free weakly coupled gauge theory. And I'm going to do the usual thing and forget about the center of mass of this brain stack. So I'm going to drop the U1 and focus on the SUN part. This is not quite correct globally, but it's good enough locally. And that's most of what I'm going to focus on. Okay, good. So I already told you that any 60 gauge theory has a U1 instanton one-form symmetry, and so does this theory. And in this theory, the instantons are literally the little strings. They are literally the infrared manifestation of the little strings in the theory, the heavy little strings. And of course, after the decoupling limit, those are the ones that come from the fundamental type 2B strings. And you can think of the source B2 that we turned on for our instanton density as the decoupling limit of the NS and SB field. Okay, this is a lot of fun, but why is it interesting? What is the story I want to tell about this? Well, what I want to do is I want to go with you through a calculation of the anomaly polynomial of this theory. This is a venerable exercise in field theory and string theory, and we're going to learn something new once we look at the anomalies. So we're in 6 dimensions, and if we're interested in local anomalies, in other words, anomalies characterized by continuous symmetries and conserved currents, then the anomaly is captured by an anomaly 8-form polynomial. So here's my anomaly 8-form polynomial, which is a kind of an 8-form made out of various characteristic classes for both the dynamical and the background fields. And I'm going to look at different terms in this anomaly polynomial and give them some interpretation. So I'm going to call the 3 parts that we're going to discuss in turn I gauge, I global, and I mixed. And these anomalies can be calculated easily from the SUSY Yang-Mills description in the infrared, because they only get contributions from massless particles. Okay, so the contribution of I gauge is by far the most famous and the most familiar. It can be calculated by evaluating a box diagram in 6 dimensions with 4 external gluons. So here I have 4 dynamical gluons on the external legs, which are the particles created by my dynamical gauge field, little f, the SUN gauge field. And this kind of anomaly in 6 dimensions can have 2 different contributions, a reducible one and an irreducible one, corresponding to either C4 or C2 squared. And both of these can be calculated by evaluating this box diagram. So you get 2 anomaly coefficients here, which I didn't write out explicitly, but these are pure gauge anomalies. These anomalies must necessarily vanish for the theory to even be mathematically consistent. So it is a true fact, and also kind of obvious from various points of view, that the gauge anomalies in this theory have to vanish. One reason it's obvious is because as far as the gauge quantum numbers are concerned, this theory is actually vector-like, it's not chiral. Good. So this theory is a consistent gauge theory in 6 dimensions, which is something we knew anyway. All right, let me move on to the next bit of my anomaly polynomial, which I'll call I global. I global is computed from a similar box diagram with gauginos or fermions running in the loop, but I'm going to take all 4 external gluons and replace them by global symmetry currents. So the anomaly diagram is very similar, but the interpretation is very different. Roughly speaking, all the dynamical gauge fields that appeared here are going to be replaced by background fields. So if you do this computation, you'll find the following contribution to the anomaly polynomial. You'll find a polynomial in all the various background fields. So here, for example, C left is the term class for the SU to the left, and similarly for C right, and P1 is the first part jargon class for the tangent bundle. So here I get some nice characteristic class in terms of the background fields. And anomalies associated to such terms in the anomaly polynomial, which only contain background fields, are now often called 't Hooft anomalies for the global symmetries of the theory. So the global symmetries are the SU2 left and SU2 right R symmetries and the Poincare symmetry. And these non-vanishing anomaly diagrams tell you that there's some interesting anomalies associated to these global symmetries, but they don't break the global symmetries. Okay? The currents themselves are conserved as operators. If you study the conservation equation of the global symmetry currents inside correlation functions, you will not find any violations at separated points. This is important for a variety of reasons. And the only way the anomaly shows up is either as a very subtle kind of C number contact term, if you really look at coincident points in flat space, or alternatively, you can actually activate the various background fields and see C number violations of background gauge invariance. Okay, so these are very interesting objects, and we like them a lot for various reasons. For example, they satisfy 't Hooft anomaly matching, which is an important tool in strongly coupled RG flows, but they don't signal a breakdown of the symmetry in any way. Good. So now I've really contrasted these two extreme cases, the gauge case where the anomaly had to vanish for consistency, and the purely global case, or the 't Hooft anomaly, which could be non-zero in an interesting way, but did not signal any breakdown of the symmetry, nor any inconsistency. And now I'm going to turn to the piece that I called I mixed. And that is going to be a little bit new. So I mixed, as you might imagine, is a piece of the anomaly polynomial that contains both the dynamical SUN gauge field of the Yang-Mills theory and some of the background fields for the global symmetries. So it comes from a loop diagram, from a box diagram that has two external gluons corresponding to the fact that this C2 of F is quadratic in the field strength. There's two gluons. And two global symmetry currents for the R symmetries corresponding to these C2s here. And if you evaluate this diagram, you'll find this anomaly coefficient. So the C2 left has an n in front of it, and the C2 right has a minus n in front of it. Okay, so the question we must ask ourselves is what to do with this kind of mixed anomaly that is half dynamical and half background. Which camp should it sit in? Does it signal a breakdown of consistency or gauge invariance, like the pure gluon diagram, or is it completely innocuous, like the 't Hooft anomaly? Well, the first thing to reassure ourselves is that this diagram does not represent a breakdown of gauge invariance. You can, in fact, regulate this diagram in a way such that gauge invariance is completely conserved, and you should do that. You have to do that. You should insist on regulating the diagram in this way. And that actually eliminates all the ambiguity that is typically associated with such anomalous diagrams. So you have to insist on gauge invariance for the dynamical gluons. And then the rest of the diagram is completely unambiguous. And what you learn is that this diagram has a non-trivial effect on the global symmetry currents. Leads to an interesting non-conservation equation. So this is what it looks like. If you evaluate the current conservation on either the left or the right R symmetry current, what you find on the right-hand side, right? This is a dimension 6 form. So you should find a dimension 6 form on the right-hand side. What you find is the anomaly coefficient, and then a mixture of dynamical operators and background fields. So roughly speaking, what you have to do is you have to apply the descent formalism to this 8 form to extract the 6 form sitting on the right-hand side here. And what you find is C2 of the dynamical gauge field, which is a non-trivial operator in the theory. But this operator isn't there by itself. It's also multiplied by 1 wedge power of the C number background fields for the left and right R symmetries. Good. So this equation, this non-conservation equation for the current, is the consequence of this non-vanishing anomaly diagram. This is just a fact, and now you have to deal with this fact. So the question is, how do you interpret it, and what is it good for? Well, the good thing is that this six-dimensional anomaly equation is a kind of straightforward generalization of a 4D phenomenon we had analyzed previously. And the correct interpretation of this equation is not that the symmetry currents for the left and right R symmetries are destroyed or broken. So this equation does not mean that the left and right R symmetries are not actually symmetries. That would be extremely weird, since they're manifest symmetries, for example, of the brane construction. And one easy way to see that is that if you want to test whether or not a symmetry is actually a symmetry, you should turn off the corresponding background fields. Just go to flat space, no background fields. And when you turn off the background fields, this term vanishes. So the right-hand side vanishes when you turn off the background fields. And that's a signal that the currents themselves are actually perfectly fine. So they're actually conserved operators, and you can use them to define conserved integrated charges. So this right-hand side does something, but it's more subtle than modifying the charges. Instead, what it does is it modifies the algebra of the currents. So it leads to a deformation of the current algebra. And you can derive that deformation by taking a variational derivative with respect to this background field. That brings down another insertion of the currents. And so you'll get something like a current OPE. And you can even integrate up this divergence to get the full OPE. I'm not going to write it out in gory detail with indices, because these things are, one form and two form currents, and they have some structure functions in front of them that are a bit annoying. But I'm going to give you the kind of the main feature of the OPE, which is roughly speaking the fusion rule. So what you learn from this equation is that two J left currents, which are ordinary one-form currents, can fuse into this operator. And remember, this operator is the two-form current, or the star of the two-form current of the instanton symmetry, which I call J sub I. So two J left currents can fuse into the instanton two-form current, and the fusion coefficient is this anomaly coefficient N. And similarly, if you take the opposite sign here, you get the fusion of two right-handed R symmetry currents into the instanton two-form current with fusion coefficient minus N. So this is a fusion rule of currents, which is perfectly consistent and which allows ordinary symmetries and higher form symmetries to mix in current algebra. And this is one manifestation of the fact that this theory enjoys a certain kind of global symmetry that is mathematically known as two-group global symmetry. Okay. Now, the usual mathematical presentation of two-group symmetry looks very different from the one that I've given you, but it'll become a little more clear in a second once I discuss the background field. But right now, this is just a phenomenon in quantum field theory at the level of current algebra. So at a very lowbrow level, you could just say that this diagram this anomaly diagram represents a mixing of these two currents fusing into the gluon-gluon operator representing this, this two form here. Okay, now in order to reinterpret this phenomenon in a way that looks a little bit more familiar, what I'm going to do is I'm going to now couple these currents to background fields. So I already reminded you of how to do that for the instanton current before. So I told you that the instanton current should couple to a background B field. And of course, we've already implicitly coupled the left and right R symmetry currents to their respective background gauge fields, which are ordinary one-form background gauge fields. And the normal thing to do, without asking too many questions, would just be to shift all of these by ordinary gauge transformations. In other words, these here would shift by D of some zero form gauge parameters, and B would shift by D some one form gauge parameter. Now, if you plug in these gauge transformations here and you integrate by parts to check whether or not the action is invariant under these gauge transformations, you have to use the current conservation equation. That's what we said before. Current conservation amounts to background gauge invariance. But here, the current conservation equation for the left and right R currents is modified in the presence of background fields. It has this non-trivial right-hand side. And because this right-hand side involves the instanton current, you can absorb this right-hand side by postulating a shift or a new transformation piece in the transformation law for the B field. And this transformation law looks like this. It's a shift of the B field by the field strengths of the R symmetry gauge field in a way that's dictated by the anomaly coefficients. Now, once you look at this formula, you can sort of forget a lot of what I've told you, because this formula is very dramatically recognizable. This formula looks like the familiar Green-Schwarz shift of a B field in string theory. So in other words, the B field B doesn't just shift like an ordinary B field, it also gets this extra shift by the ordinary zero-form gauge transformations. And indeed, at the level of formulas, this looks completely identical to standard Green-Schwarz shifts. There is one crucial difference, which is very important, which is that the ordinary Green-Schwarz mechanism is for dynamical gauge fields. So in other words, the B field in string theory is a dynamical field, and the gauge fields are dynamical fields, and everything is a dynamical field, and the gauge symmetry and all the symmetries involved are genuine gauge symmetries. So they're redundancies. Here, we're talking about global symmetries. B and A are background gauge fields, so they're not dynamical. And all these transformations that we are doing are the corresponding background gauge transformations, which are essentially the global symmetries. So the formula is like the Green-Schwarz mechanism, but it's a Green-Schwarz mechanism for background fields. Now, it was appreciated by a whole group of people, starting maybe with Baez and Schreiber and others, that the Green-Schwarz mechanism in string theory could be understood in terms of two-group symmetry. And in that case, that was a two-group gauge symmetry. And similarly, what I'm telling you about here is a Green-Schwarz mechanism for background fields, which is why what I'm talking about is related to two-group global symmetry. Okay. Any questions so far? Okay, so what I've told you so far is, in a very particular example, that mixed gauge global anomalies of the type we encountered in the maximally supersymmetric Yang-Mills theory deform the global symmetry of that theory into a two-group at the level of current algebra. And it's followed from doing this anomaly computation with two global symmetry currents and two gauge fields. Now, it's not difficult to believe that this is very generic in 60 gauge theories. 60 gauge theories are generically chiral. And we saw that this phenomenon even happens in the 1,1 little string theory, or the 1,1 maximally supersymmetric Yang-Mills theory, which is about as non-chiral as it gets. And even there you encounter this phenomenon. So we checked a whole bunch of other string theory examples and found that this phenomenon occurs. And then these authors actually went and did a systematic check of all sorts of examples that have been constructed using F theory, and systematically checked that the vast majority of them have non-trivial two-group symmetry. So the picture that emerges from this analysis is that all little string theories have a one-form symmetry, a U1 one-form symmetry. This is essentially the little string charge, the level of the supersymmetry algebra. And generically, it's part of a two-group. Generically, it mixes with ordinary global symmetries and turns into a two-group. And one thing you can do, for example, is you can match this two-group across dualities. So I said in the beginning that little string theories enjoy dualities, for example, T-dualities, and you can match the two-group symmetry across these dualities. So that gives you a new check of the dualities but it also gives you confirmation that this two-group symmetry that we found by analyzing the low energy effective quantum field theory is actually a legitimate property of the full theory. Good. So this is the story that I wanted to tell about the string theories and introducing two-group symmetry in that context. In the rest of the talk, what I want to quickly sketch is how this story is modified if the theory that you flow to in the infrared is a superconformal quantum field theory. Can you please remind me how much time I have left since we started a little bit late?
At least 15 minutes.
15 minutes? Okay, thank you. Okay, so what happens in superconformal field theories? Well, there's a few things that necessarily happen in superconformal theories that did not happen in the example that we discussed before. And that's going to make a lot of difference. So it's true, and I reminded you in the beginning, that many interesting superconformal field theories on their tensor branch have non-abelian gauge fields. So they are effective gauge theories at low energy. However, it turns out that whenever gauge fields occur on the tensor branch of a superconformal field theory, they always couple to the tensor multiplet in an interesting way. So let me remind you that the reason the tensor branch is called the tensor branch is because it's parametrized by the bevs of real scalar fields phi living in a 1,0 tensor multiplet together with some fermions and a chiral dynamical B field. So little b here is a dynamical B field, not the background field big B that we discussed earlier. And all superconformal field theories necessarily have a coupling of this form whenever there's a dynamical gauge field around. So if little f is a dynamical gauge field with second Chern class C2 of little f, then there's always a coupling of this form to the dynamical B field in the 1,0 tensor multiplet. It looks formally identical to the coupling I wrote down before, but before this B was a background field. It didn't do anything. It wasn't dynamical. Now this little b here is dynamical, and this coupling is much more dramatic. The reason this term is always present in a superconformal theory is because it has all sorts of important functions to perform. The canonical way to explain why this term is always there with non-zero coefficient C is because it's required to cancel certain gauge anomalies. Right? Because it's a Green-Schwarz term, it contributes a term to the gauge anomaly, which is effectively the square of this term. So we get a contribution that looks like C times the second Chern class squared to the pure gauge anomaly of the theory. And this coefficient C is non-zero because it has to cancel a certain one-loop contribution involving fermions that gives rise to an anomaly of the same form, but with coefficient minus C. So this is unavoidable in superconformal theories, and this is how Seiberg argued that this coupling has to be there. Okay, so the moment you appreciate that this coupling has to be there, then the role of this current, which before we said was a global two-form symmetry current, changes. If you take a global symmetry current and you couple it to a dynamical gauge field, then it's no longer a global symmetry current. It has been gauged, right? It's like taking a global symmetry and coupling it to QED. The thing that used to be the global symmetry is now the electric charge, and it's no longer a global symmetry in the same sense. So this coupling gauges the instanton two-form current, and it destroys the one-form symmetry that I've talked about in the first half of the talk. So that suggests that this one-form symmetry doesn't actually exist in superconformal field theories. And that interpretation is correct, and you can give a completely independent argument for that. So at the superconformal point, all operators have to sit in unitary multiplets of the superconformal algebra. Depending on how much supersymmetry you have, you might have different algebras. And you can classify all ways in which conserved currents can appear in multiplets, in unitary multiplets of the superconformal algebra. This is something we did in this paper. And what you find is that in 6 dimensions, with any amount of superconformal symmetry, conserved two-form currents like Ji cannot arise. So no unitary 6D SCFT has such an operator, has such a conserved two-form current. And therefore, it doesn't have continuous one-form symmetries like the instanton symmetry. And a fortiori, it does not have the two-group symmetries that involve mixing with this one-form symmetry. So essentially, none of the phenomena that I talked about in the first half of the talk can arise in superconformal field theories. Good. Let me skip this comment about the dilaton. So far from kind of making this case boring, it actually leads to an interesting story. Because I tried to argue before that the kind of mixed anomalies that lead to two groups are quite generic in 6 dimensions, right? They come from these box diagrams, and whenever these anomalies are non-zero, and they are generically non-zero, you have such a two-group symmetry. So now I'm telling you that in superconformal theory, there's some sort of magic where the two-group symmetry always ends up disappearing at the end. So how does this happen? Well, it actually involves a delicate cancellation that allows you to compute certain things or deduce certain things that you couldn't otherwise have deduced. So the absence of two-group symmetries in SCFTs actually has non-trivial consequences. So let me briefly sketch how that works. I already told you that in superconformal theories, the instanton density is gauged by the dynamical B field on the tensor branch, and there's this Green-Schwarz coupling involving only dynamical fields. But because you have the dynamical B field, you can also couple in other Green-Schwarz-like terms that couple to background fields. So B doesn't necessarily only couple to the dynamical C2, it can also couple to a linear combination, suitably quantized linear combination of all the various background C2s or P1s. So for example, here I've sketched the appearance of a Green-Schwarz term involving the dynamical B and the background instanton density for the SU2R symmetry with some coefficient K. And you can include other such terms here. So these are background fields for global symmetries. And this coefficient K is some coefficient that you don't necessarily know how to compute. Some coefficient in the low energy effective action, but it only appears when you turn on background fields. Okay, so what does the Green-Schwarz mechanism do? The Green-Schwarz mechanism tells you that whenever B, which is chiral, remember, couples to something, right, that something squared contributes to the anomaly polynomial. So I have to take this quantity here that I'm circling, square it, and that's the contribution of this Green-Schwarz term to the anomaly polynomial. So when I compute the square, of course, I get the pure gauge term, which we already discussed. I get a pure C-number term, which is an 't Hooft anomaly, but I also get a mixed term, right? Because I'm squaring this binomial or multinomial. And the mixed term involves coefficients C and K, and also a mixing of the gauge and global symmetries. So whenever you have such a mixed term, whenever you have such a Green-Schwarz term, a mixed term of this kind is always generated. Okay, but remember that such a mixed term inevitably led to a non-trivial two-group symmetry, right? And I just told you that if you're in a superconformal quantum field theory, there are no two-group symmetries. So this mixing has to cancel, it has to vanish at the end of the day. And the way this happens is that this contribution to the mixing, which comes from this Green-Schwarz term, has to also cancel against one-loop diagrams coming from massless particles in the infrared, right? Just like this contribution to the Green-Schwarz mechanism had to cancel against gauge anomalies of massless particles in the infrared, this mixing, which represents potentially a non-trivial two-group, has to also cancel against massless particles in the infrared. But it cancels for completely different reasons. the reasons don't have anything to do with gauge anomalies. They have to do with the statement that I made before, that 6D superconformal theories, unlike little string theories, are not allowed to have these two-group global symmetries. So there's a kind of interesting anomaly cancellation condition which emerges from this condition. And that anomaly cancellation condition allows you to completely fix this unknown coefficient K in terms of pure infrared data that only involves the massless fields on the tensor branch, which you know. In any construction of the theory, you know it, in any string construction and field theory construction. Good. So this procedure for calculating these kind of anomaly coefficients like K was proposed a while ago in a paper by these authors. And it was clearly correct, but it was very mysterious. And here you see that the justification involves a somewhat non-trivial argument going by the route of two-group symmetry and its absence. So once you are able to calculate these Green-Schwarz coefficients, you can, for example, compute the entire anomaly polynomial of the UV quantum field theory with the superconformal quantum field theory, knowing essentially only the massless fields in the infrared on the tensor branch, which is what these authors did. This is, of course, much more than you're typically entitled to. Good. So I don't have time to really explain in detail some of the things that you can apply this understanding to, but let me briefly mention in the last couple of minutes one application involving the A theorem in 6 dimensions. The A theorem in even dimensions is the statement that the conformal A-type anomaly of conformal field theory is monotonically decreasing under RG flows. My pen stopped working. Okay, maybe I'll stop circling things. So if you have an RG flow interpolating between two different CFTs in the UV and in the IR, then the A anomaly decreases under that flow. And the intuition that goes along with that is the statement that A, roughly speaking, counts the number of effective degrees of freedom along the RG flow. So this is a famous statement in even dimensions, which is a theorem in 2D and in 4D, but not in 6D. There's no general proof of this statement for 6D RG flows, at least not for non-supersymmetric flows. With supersymmetry, you can do better. And we had an argument a while back that for supersymmetric RG flows, the change in the A anomaly is essentially a perfect square and therefore positive. So that implies the A theorem. However, the A theorem in itself does not imply, trivially, that the total A anomaly of a given CFT is positive. Roughly speaking, you might think that it does, because you could, for example, try to take a CFT and flow to a trivial gap theory in the infrared. And if you do that, then the infrared theory doesn't have any A anomaly. And therefore, delta A is the same as the A of your UV CFT, which is therefore positive by the A theorem. But in chiral theory, it's not always possible to flow to a gap phase. You might be prevented from doing that by various anomaly considerations. So it actually turns out to be a non-trivial question to prove whether or not 6-dimensional superconformal field theories have positive A anomalies. Okay, so I won't have time to explain a little bit the puzzle that arises in this context, but let me just say that this question can be answered if you have exquisite control of the 't Hooft anomalies of the theory. The reason is that there's a universal formula that relates the A anomalies to 't Hooft anomalies for the global symmetries, in particular the R symmetries and the diffeomorphism symmetries, just like in 4 dimensions. And if you control well enough the 't Hooft anomalies of your theory, you also control the A anomaly. So you can prove bounds on A and delta A if you can do that. And what I essentially explained to you previously is that the absence of two-group symmetry in SCFTs gives you a sharp way to calculate all of its 't Hooft anomalies and Green-Schwarz terms. And so that translates directly into the ability to compute the A anomaly of the 6D theory. And it turns out you can give a nice and relatively easy proof that it's always positive. So since I'm out of time, I'll stop here. Thank you.
Any question?
I maybe have a naive question. Thanks for a fantastic talk. I was curious if you had any interpretation of what such a two-group symmetry is telling me, or like in particular, it's coming from this OP of R symmetry currents, if I remember correctly.
More generally, it could be any standard one-form current fusing into a higher form current. Yeah.
But if I think, for example, about like a brane world volume theory, then I have sort of a geometric idea about what those R symmetry currents are doing, or what symmetries they generate. I guess I was wondering if there's any sort of geometric intuition, like for example, just in that case, for what this two group is about, or what this deformation is telling me about the string background.
Well, so I can give a few very lowbrow answers. You might be asking for something more sophisticated, which I would also like to know about. But the lowbrow answer is that the two group is not a modification of the symmetry at the level of charges. So if you look at the commutators of charges in the symmetry algebra, it does not appear to be modified.
Yeah.
Okay. So the R symmetry, for example, still looks like it's SO4 and it doesn't look like anything funny is happening. So instead, this is a modification of the current algebra. So in order to detect it, you need to ask some slightly more local question. And there are many ways of asking such a local question. For example, looking at the OPE of the currents, but a different way of asking the question is to actually turn on a non-trivial B field. And when you do that, right, as is familiar from the string theoretic Green-Schwarz mechanism, when you turn on a non-trivial B field because of this transformation rule, it'll mix with the A field. Okay, so if you allow yourself to study configurations where these fields are turned on, you will see this mixing. And of course, in a given string construction, this might be very, very obvious. For example, in the brane construction I reminded you of for the 1-1 little string theory, right? I said that the B field was the actual string theoretic B field. And this Green-Schwarz shift is actually the string theoretic Green-Schwarz shift.
Sure.
The only thing that happens in the decoupling limit is that they get frozen and become background fields. So any intuition you can derive from that, you can transplant to this case.
Sure, okay. Thank you.
Any other question?
Can I read a failure of associativity in the current algebra on in this deformation? Is it like a failure of associativity or of a Jacobi identity, or?
Yeah, so it's not the Jacobi identity for charges. As I said, the algebra of charges is not modified, but there is a failure of associativity if you ask a sufficiently refined question. So you might be referring to the fact that two groups in general are characterized by a non-trivial associator. And you can see that here as well. If you wish, it's all encoded in the OPE of these currents. But if you want to see the actual associator, what you can do is you can integrate the currents to make charges. But then you don't just study the Jacobi identity. What you have to do is you have to study certain F moves, where you move several symmetry surfaces past each other. And if you do that in two different ways, right? The way you usually try to derive the Pentagon identity, and then you'll see the associator come out. And the reason the associator comes out is because as you move these surfaces past each other, at various points they'll intersect, and at the points of intersection, the right-hand side of the current algebra will kick in. Right, precisely when the two currents collide, when the two surfaces collide, then you can have an effect. Yeah.
Other question? All right, so if there are no further questions, I thank again the speaker. Thank you very much.
Thank you.
So we're done for today.
Yeah, we're going for dinner now, Thomas.
Yeah, have fun.
Well, thank you for coming anyway.
Yeah, thanks for inviting me.
Come back sometime. So everybody knows where we can go? Meet at 8 at Weißer Punkt. 8 o'clock. 8 o'clock, Weißer Punkt.